The universe is not just vast, it's also in constant motion. Galaxies are moving away from one another, and space itself is stretching. But if everything is expanding, what happens at the very edge? Is there a border? And if so, what's beyond it? In this video, we'll explore what scientists mean when they talk about the edge of the universe, why the idea of a border is tricky, and what current research can tell us about the farthest reaches of space. Before we begin, let us know in the comments section where in the world you're watching from and what time it is there now. Then, settle in as we uncover what exists on the borders of the expanding universe. At the farthest reaches of the universe that we can observe lies something both mysterious and breathtaking. It is not a wall, nor a final border where everything suddenly ends, but rather a kind of cosmic horizon. This horizon is the limit of what our eyes and our instruments can see. Beyond that invisible line, the universe does not stop. It continues endlessly, stretching into spaces that light itself has not yet revealed to us. The reason we cannot see farther is simple. Light from those unimaginably distant places has not had enough time to reach Earth. This limit exists because the universe has been expanding ever since it began. Some galaxies are racing away from us at such extreme speeds that the light they give off is unable to keep up. These galaxies exist, they are real, but to us they remain hidden because their light has not yet arrived. It is similar to standing at the edge of a vast, endless sea. You can look out as far as your eyes allow, and the horizon appears calm and far away. You know, however, that the ocean does not stop at the horizon. There are more waves, perhaps distant islands, and maybe even entire continents lying beyond. The only reason you cannot see them is because your sight does not stretch that far. In the year 2023, scientists made a discovery that shocked the world of astronomy. A study published in the journal Nature, using data from the powerful James Webb Space Telescope, revealed something that current ideas about the universe could not easily explain. The telescope found 6 enormous galaxies that appeared to have formed only about 600 million years after the Big Bang. This was an astonishing discovery because scientists believe that galaxies so massive should have taken billions of years to grow. The universe itself is thought to be about 13,800,000,000 years old. Yet here were galaxies that appeared far too large and far too developed for such an early time. According to the best calculations, these galaxies should have been at least 10 times smaller, or perhaps even 50 times smaller, than what was observed. The problem is that, in theory, there should not have been enough ordinary matter, the very stuff that creates stars and planets, to form galaxies of that size so soon after the birth of the universe. If this finding is correct, it could force scientists to rethink one of the most fundamental ideas in cosmology, the true age of the universe. Some researchers have even suggested that the universe may not be 13,800,000,000 years old at all, but perhaps an extraordinary 26,700,000,000 years old, nearly twice as old as most people believed. If true, this would change our understanding of space and time in ways we can barely imagine. Erica Nelson, one of the scientists who studied the data, explained that even if just one of those galaxies turned out to be real, it would stretch the limits of what we thought was possible. At present, no existing scientific model fully explains this strange discovery. Some have proposed an idea called dark time, which suggests that galaxies and other cosmic structures might have formed much faster than anyone ever expected. If this theory is correct, scientists may have to rewrite the story of how the universe grew and changed over billions of years, even though we cannot yet say with certainty what the universe looks like in its entirety. We know that if it does have edges, whether sharp or unclear, it might, in theory, be possible to reach them. But what would that journey feel like? For centuries, people have asked similar questions. Ancient civilizations wondered about the center and the outer limits of the universe. In the 19th century, an engraving showed how people in the Middle Ages imagined a boundary to existence, beyond which lay strange and mysterious forces that controlled everything. To understand how light and distance work in space, think of the red supergiant star Betelgeuse. When we look at it, we are not seeing it as it is right now. Instead, we are seeing it as it was about 500 years ago, because that is how long its light takes to reach Earth. It is possible that Betelgeuse has already exploded in a supernova, but we will not know until the light from that event finally arrives here. Gravity behaves in a similar way. The pull of the sun does not reach us instantly. It takes about 8 minutes and 20 seconds for the Sun's gravity, like its light, to travel across space to Earth. That means if the Sun were to suddenly vanish, our planet would keep orbiting as though nothing had happened for those 8 minutes and 20 seconds. Only after that delay would Earth and the other planets drift into darkness. The same principle applies on a larger scale. The Andromeda Galaxy, the largest galaxy close to ours, is moving towards us at an incredible speed of about 400,000 kilometers per hour. But because we are looking at light that left Andromeda long ago, it is actually about 900 light-years closer than it appears. To give perspective, the nearest star to the Sun, Proxima Centauri, is a little more than 4 light-years away. Even with the fastest spacecraft we can currently build, it would take tens of thousands of years to reach it. So discovering that Andromeda is hundreds of light-years nearer than it seems is a major revelation. When we observe the universe, we can only see as far as light has had time to travel since the beginning of everything. The farthest light ever detected comes from about 46 billion light-years away. But if the universe is only 13,800,000,000 years old, how can we see farther than that? The answer lies in dark energy and the rapid expansion of space itself. The light from those faraway regions did not travel here in a straight, unchanged line. Instead, space has stretched as the universe expanded, allowing us to see far beyond what the universe's age might suggest. That is why we can look out and detect light from 46 billion light-years away in every direction. The observable universe, therefore, has a limit, but the actual universe almost certainly stretches much farther. Whether it ends at some unknown border or goes on forever is a question still waiting for answers. Astronomers have even imagined what it would be like to try to reach the universe's edge. David Kipping from Columbia University suggested building a spaceship that could accelerate forever at a steady rate of 10 meters per second squared. At that speed, the crew on board would feel the same pull as Earth's gravity, so they would not float. They would feel like they were standing on solid ground. To compare, Earth's gravity is about 9 8/10 meters per second squared, so rounding it to 10 makes the calculations easier. With this acceleration, the ship would gain speed rapidly. In just 1 second, it would be moving at 10 meters per second. In 2 seconds, 20 meters per second. After 1 hour, its speed would reach over 35,000 meters per second. In only 2.5 hours, it would pass the Moon. In 1 week, it would fly past Saturn. After 11 days, it would pass Neptune, the farthest planet in our solar system. And in just 15 months, the ship would travel a distance equal to 1 light-year. But then the rules of Einstein's special theory of relativity would start to change everything. While it might seem like the ship could continue speeding up forever, there is one unbreakable law: nothing with mass can ever reach the speed of light. In experiments at the Large Hadron Collider, protons have been accelerated to speeds extremely close to that of light, nearly 299,792,455 meters per second. But no matter how much energy scientists use, they can never quite reach the exact speed of light. If this physical law did not exist, the ship would reach light speed in just 45 days. Instead, as it draws closer, strange things happen. To observers watching from far away, the ship would seem to slow down as it nears the speed of light. To those inside, however, everything would appear normal. Time for them would feel unchanged, but they would notice that time outside the ship seemed to move faster and faster. When the ship reached 87% of the speed of light after 15 months, time would already be passing much more slowly for the crew compared to everyone outside. The closer they got to light speed, the greater this effect would become. This phenomenon, predicted by relativity, shows just how strange and extraordinary the universe is when we push against its deepest limits. On the 15th day of October in the year 1991, something happened that left scientists speechless. A particle from deep space, so small that no eye could ever see it, struck Earth. Yet this was not just any ordinary cosmic ray. It carried such an unbelievable amount of energy that the scientists who studied it gave it a dramatic name, the oh my god particle. Once you hear what made it so extraordinary, you'll see why they reacted with such astonishment. This particle, tiny beyond imagination, held within it the same amount of energy as a baseball flying through the air at about 94 kilometers every hour. Just think about that for a moment. Something invisible to us, smaller than the tiniest speck of dust, carried the same punch as an object large enough to fit in your hand being thrown at a fast speed. That comparison alone makes it hard to believe, but what truly shocked scientists was not just the energy, it was the speed. This particle was travelling at a speed so close to the speed of light that the difference was almost impossible to measure. In numbers, it was moving at 99 point, followed by 29s, and then a 5, all as a percentage of the speed of light. That means it was missing the absolute speed limit of the universe by only the smallest imaginable fraction. According to everything we know about physics, nothing with mass should ever reach that close to light speed, and yet, here was this one lone particle defying all expectations. Even now, decades later, no one knows exactly what could have given this particle such an extraordinary push. What kind of cosmic engine, what kind of event or force out there in the universe was powerful enough to hurl this tiny particle across space with so much energy? That mystery still remains unsolved. However, new observations from the Telescope Array project have given scientists a clue. They suggest that the particle may have come from a region of the sky about 20 degrees wide, in the direction of the group of stars known as Ursa Major, the Great Bear. That is all the evidence we currently have, but even that small clue only raises more questions than it answers. Just thinking about the possible cause is enough to make your skin tingle with wonder. One of the strangest aspects of this story is how time itself behaves when something moves so close to the speed of light. At that extreme speed, time for the particle slowed down compared to time on Earth. The effect was so powerful that from the perspective of the particle, time had almost come to a halt. In fact, its time slowed down by a factor of 300 billion compared to ours. To see what this means, let's use an example. The Andromeda Galaxy, the nearest large galaxy to our own, is about 2.5 million years away if you travel at the speed of light. If humans tried to reach it, it would take them 2.5 million years to get there. But for this particle, moving so close to light speed, the same journey would not feel like millions of years. For it, the trip would last less than 5 minutes. Now let's stretch this idea even further. What if, instead of a particle, a spaceship could travel at such an incredible speed? What would happen if it kept moving away from Earth without ever stopping? There is a strange boundary in our universe, an invisible line about 8.3 billion light-years away from us. If a spaceship ever crossed that line, it would be lost forever, not because of a physical barrier, but because of the way space itself stretches. Beyond that distance, space is expanding faster than the speed of light. This means that no matter how fast the spaceship tried to come back, no matter how much energy it used, it would still drift farther and farther away. The ship would not be breaking the cosmic speed limit. Instead, the fabric of space itself would be carrying it beyond reach. To help understand this, think of a toy slinky. When you stretch it, each coil moves only a little, but the coils at the ends quickly become very far apart. In the same way, galaxies are not racing through space faster than light. Instead, the space between them is stretching at such a speed that they end up farther and farther apart. So if a spaceship ever crossed that 8.3 billion light-year horizon, its crew would be trapped. No effort, no technology, no amount of energy could bring them home. They would be lost forever in the endless night of space. It is a haunting thought, drifting beyond the point of no return. The universe grows even stranger when we think about distances on the larger scale. The part of the cosmos we can observe with telescopes, the visible universe, is about 46 billion light-years across in every direction. And because the universe keeps expanding, this size is only getting larger. Scientists expect that one day, this visible region will stretch to about 61 billion light-years. But there is a catch. Just because we can see something does not mean we can ever reach it. Dark energy, a mysterious force that is speeding up the growth of the universe, has divided space into different zones. Galaxies within 15 billion light-years are still reachable, at least in theory, if we could travel at the speed of light. Galaxies farther away than that, but still within the 46 billion light-year boundary, can still be seen by our telescopes. But we can never get to them. They are being pulled away too quickly. Even more puzzling, there are galaxies already beyond 46 billion light-years. Right now, they are completely hidden, and no telescope today can detect them. Yet, in the far future, their light will finally reach Earth, and humans, if still alive, will get a glimpse of them for the first time. But beyond 61 billion light-years, there are galaxies that will remain hidden forever. No future generation, no matter how advanced, will ever see them. They lie beyond the ultimate horizon. To see how dramatic this expansion is, consider one of the farthest galaxies we know of, GNZ 11. The light we see from it today began its journey 13.4 billion years ago. Only 400 million years after the Big Bang. But because of the stretching of space, GNZ 11 is no longer where it appears to be. Today, it is actually 32 billion light-years away. We can still see it for now, but not for long. In time, its light will vanish. The rays GNZ 11 is sending out right this moment will never reach us. Space is expanding too quickly, pulling it away forever. And this same fate awaits countless other galaxies. The numbers are staggering. Scientists estimate that more than 96.7% of the galaxies we can see today have already slipped beyond our reach. Even more alarming, 98.6% of all the galaxies humanity could ever hope to observe are already gone, carried away by the expanding universe. In total, the universe should hold around 4,700 billion galaxies within the region that could, in theory, be seen. Yet out of this number, 4,634 billion are already lost to us. That leaves only about 66 billion galaxies we can ever hope to reach. And the loss does not stop there. Every single second, about 60,000 stars vanish from our visible universe, pulled away into regions we will never see again. That means tens of millions of stars are disappearing from sight every single day. Stars that once shone within our cosmic neighborhood are being erased from our view forever. The universe is not only vast, it is slipping away from us at an unstoppable pace, leaving behind mysteries that may never be solved. Many of the stars we see shining above us might not even exist anymore. Some of them could have burned out and died millions or even billions of years ago, yet their light is only now arriving on Earth after travelling across enormous distances. That is already an incredible thought, but when we scale it up to the entire universe, the picture becomes even more mind-bending. There are whole galaxies that, right at this moment, are vanishing from our reach, not because they are exploding or being destroyed, but because the universe itself is expanding so quickly that any new light they send out will never be able to reach us. For us, those galaxies might as well no longer exist. They still continue their existence somewhere in the vastness of space, but for our part of the universe they are gone forever. We cannot visit them, cannot communicate with them, cannot watch how their stories unfold, and they cannot affect us in any way. In our reality, they are sealed away, cut off completely, as though erased from our version of the cosmos. If the mysterious force driving the universe to expand keeps getting stronger, then even the galaxies closest to us will one day drift away into the void. Slowly, every galaxy will find itself stranded in total isolation. Stars within them will eventually run out of fuel and fade, leaving behind dark, lifeless remnants. The building blocks of everything we know, planets, people, molecules, and even atoms themselves, will one day break apart. Even black holes, which for a long time were thought to last forever, will not escape this fate. They will shrink and vanish through a slow process known as Hawking radiation. The time it takes for this to happen is so unimaginably long that our minds struggle to make sense of it, but in the end, even the most powerful black holes will disappear. All that will remain is empty space stretching endlessly, filled only with the mysterious presence of dark energy. Dark energy is one of the strangest ideas in modern science. Gravity pulls matter together, but dark energy does the opposite. It forces space to expand. The strangest part is that as the universe stretches and grows emptier, dark energy does not weaken. It either stays the same or perhaps even becomes stronger. This creates a kind of endless loop. The universe expands, which creates more space. The more space there is, the more room dark energy has to push, which makes the universe expand even faster. Over time, this cycle ensures that the expansion will speed up more and more. Eventually, things happening in one part of the universe will have no effect on anything else. Distances will become so vast that even light, which is the fastest thing in existence, will not be able to cross the gulf. Now imagine something remarkable. Suppose we built a spaceship capable of moving almost as fast as light itself. If the crew inside travelled for what they measured as 200 years, then for the rest of the universe, an almost impossible amount of time would have passed, about 10 to the power of 41 years, which is a 1 followed by 41 zeros. By that far-off time, the universe would look unrecognisable. Space would have stretched so greatly that the ship might be the only thing left in its corner of the cosmos. There would be no stars, no planets, no galaxies, only endless darkness. The crew would find themselves flying through a universe that had already gone completely empty. Could they ever reach an edge of the universe? The answer is no. Even at near light speed, they would never get there, because the universe has no edge to find. Space itself keeps expanding faster than they could ever travel, placing the idea of an edge forever out of reach. This leads to a very strange and difficult idea. What if the universe has no edge but still is not truly infinite? For thousands of years, humans have wrestled with the question of whether the universe goes on forever or whether it ends somewhere. Over 2,000 years ago, the Greek thinker Artitas raised a question that still makes us pause. If someone stood at the very edge of the universe and threw a spear, what would happen? Would it bounce back off some invisible wall? If it did, what lies beyond that wall? And if the spear went through, then space must continue on. By this reasoning, the universe must stretch forever. This puzzle troubled philosophers and scientists for centuries. But perhaps the answer is not simply endless or not endless. Perhaps the universe can have no boundaries and yet still be limited in size. In the 19th century, the great mathematician Carl Friedrich Gauss began exploring this very possibility. For most of history, it was believed that the angles inside every triangle must always add up to exactly 180 degrees. This is true on a flat surface, but Gauss realized space might not actually be flat at all. Think of standing on the surface of a giant sphere like a planet. If you draw a small triangle on the ground, its angles still add up to 180 degrees. But if you draw a huge triangle stretching across a large part of the sphere, the sum of its angles will be greater than 180 degrees. The reason is that the surface is curved. Gauss wondered whether space itself might also be curved. To test this idea, he secretly measured the angles of a massive triangle formed by 3 mountain peaks in what is now Germany. He wanted to see if their angles added up to more than 180 degrees. The difference, however, was so tiny that it could not be proven with the tools he had at the time, so he never published his findings. Decades later, Albert Einstein's theory of general relativity showed that Gauss had been on the right track. Space is indeed curved by the force of gravity. Careful measurements later confirmed that even near Earth, the angles of a triangle can add up to slightly more than 180 degrees, about 180.2 degrees. This discovery raised a profound possibility. If space is curved on the larger scales, the universe could be finite in size but still have no edges. Think about the surface of a balloon. A creature living on its surface would never find an edge. To them, the world would feel endless, yet the balloon still has a definite size. If that creature kept moving in one direction, eventually they would circle around and end up back where they started. If our three-dimensional universe is shaped in a similar way, then it might not stretch on forever in a straight line, but instead fold back on itself. To us, it would seem endless, but in reality, it could be closed in a shape we cannot easily see. This leaves us with a breathtaking picture. The universe is expanding faster and faster, driven by the strange and invisible force of dark energy. Galaxies that we see today will one day slip out of view forever. In the very distant future, all that remains will be a vast, silent emptiness. We usually think of the universe as going on forever in all directions, but perhaps that is not quite true. Scientists are still trying to understand the real shape of the universe, not just how it appears from our limited viewpoint inside it. A key clue lies in the idea of curvature, a mathematical concept that might reveal whether space truly extends without end or instead loops back on itself. At first, such ideas seem impossible to grasp, but we only need to look at our own Earth for a comparison. If you walk in one direction on Earth, you will never find an edge. Instead, you will eventually return to the very spot where you began. Up close, Earth's surface feels endless, but from a wider view it is a closed, curved shape. Perhaps our universe works in a similar way, hiding its true nature within the fabric of space itself. Now, think of the same idea, but in three-dimensional space. Could the whole universe be bent so that if you moved in a straight line for a long time, you'd end up back where you began? It's a very hard thing to picture, even for the smartest scientists. Our minds can't really see it, so we use math to help us guess what might be true. Over the years, scientists have done a lot of study on this topic and have found not just one but 18 different possible shapes, or forms, for the universe. These possible shapes fall into two main groups, orientable and non-orientable universes. To understand the difference between these two types, Let's look at a strange two-dimensional shape called the Mobius strip. You can make a Mobius strip by taking a long strip of paper, giving it one twist and then joining the two ends together. What makes this shape so special? If you put a dot on the strip and start drawing a line along the surface without stopping, you will eventually return to where you started, but flipped. That means the direction is reversed. If you had written something on one side of the strip, when you come back to your starting point, the writing would look like a mirror image. In math, surfaces like this are called non-orientable, meaning they have paths that flip the direction of things moving through them. On the other hand, shapes like a ball or a donut, called a torus, are orientable, which means they do not flip anything. Now, think of the entire universe being shaped like a Mobius strip, but in 3 dimensions. If this were true, something very strange would happen. If you travelled in a straight line far enough, you would end up back where you started, but everything would be reversed, like a mirror image. This may sound like something from a science fiction story, but in math, it is a real chance. However, most scientists who study the universe do not believe we live in that kind of universe. One reason is that if the universe were non-orientable, there would likely be places where normal matter and antimatter, its opposite form, would meet. This would create energy that we could detect, but so far we haven't seen anything like that. That doesn't mean it's completely impossible. It could still be true in parts of the universe that are far beyond what we can see. One way scientists check these ideas is by measuring how space bends over huge distances. Near heavy things like stars and black holes, space is definitely bent. But when we look at space on a much larger scale, the data shows that the universe is very flat, at least in the parts we can see. If the universe is really flat, that has big results. It means the universe could go on forever, because a universe that goes on without end would look flat when seen on a very large scale. And this leads to some amazing ideas. A scientist named Max Tegmark studied this in his book Our Mathematical Universe. He worked out that the number of ways particles can arrange themselves in the part of the universe we can see is about 10 raised to the power of 10 raised to the power of 118. That's a number so huge we can't really picture it. But if the universe really is endless, then something amazing must be true. Somewhere out there, way beyond what we can see, there must be another Earth exactly like ours. Think of drawing a straight line from Earth in any direction. If you travelled a distance equal to 10 raised to the power of 10 raised to the power of 118 times the size of the observable universe, you would, in theory, reach a copy of Earth, with a copy of yourself thinking the same thoughts right now. This idea might seem even stranger than a universe with mirrored space, but unlike the Mobius strip idea, where reality is flipped, an endless universe means that every possible arrangement of particles must happen somewhere, no matter how unlikely. Now let's take this thought even further. What happens if space is not just endless, but time is endless too? The answer is simple but deep. In a universe that has no end in space or time, everything that can happen will happen, eventually. Even if we think of a huge empty part of space with no particles at all, modern science says that this space is never completely empty. Tiny energy fields, called quantum fields, are always shaking a little. These tiny shakes, called quantum fluctuations, are a basic part of how the universe works, thanks to Heisenberg's uncertainty principle. If you wait long enough, these tiny shakes could cause very strange things to happen, like whole structures forming by chance, or even a whole new universe appearing from nothing. As wild as that sounds, it's actually something that modern physics predicts. Think of a universe so huge and endless that even the most impossible things will happen, not just once, but many times, if you wait long enough. You might think, are you seriously saying that if we wait long enough, something like a grand piano could appear out of nowhere in the middle of empty space? As strange as it sounds, some of the top scientists in the world, Anthony Aguirre, Sean M. Carroll, and Matthew C. Johnson, have studied this idea seriously. They even did the math, and found that if you waited for a time so long it would make the current age of the universe seem like the blink of an eye, something like 1 trillion times longer, you would eventually see that piano show up out of thin air. As hard as this is to believe, it follows from what we currently know about the laws of physics. The less likely something is, the longer you have to wait. But in a universe that lasts forever or goes on forever, or both, even the most unlikely things will happen. Not just once, but an infinite number of times. That's the strange truth about infinity. If time truly never ends, then our universe will repeat itself endlessly. you will watch this exact video again, not just once, but over and over forever. Some people find this exciting, others might find it disturbing. It makes us wonder, is the universe really infinite, or does it have some kind of edge? Some scientists think the universe could still be finite, just extremely large and shaped in ways we haven't worked out yet. The tools we use today tell us the universe seems flat, with an accuracy of 99.75%. But if it's not perfectly flat, then it must be at least 400 times bigger than the part we can see, stretching across a mind-blowing 37,200,000,000,000 light-years. But here's the twist. Even if the universe is closed, that doesn't mean it bends the way we might expect. Think about a cylinder. It looks flat from the side, straight lines stay straight, but it can still go on forever in a loop. The universe might work the same way. Some scientists even think the universe could be shaped like a four-dimensional torus, a shape where space seems flat, but if you go far enough in a straight line, you end up back where you started. A four-dimensional sphere would behave differently. Angles in a triangle would add up to more than 180 degrees, and straight lines would eventually meet. As three-dimensional beings, we may never fully understand what the universe really looks like. To see it clearly, we would need to live in 4 dimensions. And here's a surprising idea. The edge of the universe is not far away. It's all around us. To see why, think of a world that only has 2 dimensions, just a flat surface that might go on forever or loop around. In this flat world, there are 2-dimensional beings who can't see the 3rd dimension. To them, their world feels complete. But from our view in 3 dimensions, we can see everything about them. We could see every part of their world, even the edges that they can't see. The edge of their world is invisible to them but clear to us. Now apply that to our world. The 4th dimension is not some far-off place. It's all around us, touching every part of our universe. We are surrounded by it, but we can't touch or see it. It is the true border of our universe, always there, but just out of reach. The part of the universe that we can see from Earth is called the observable universe. It is shaped like a giant sphere with Earth and the solar system sitting right at the centre. Everything inside this sphere is made up of matter that has sent out light or other forms of energy since the very beginning of the universe's expansion. That light and radiation has had enough time to travel across space and finally reach us. This is why we're able to study stars, galaxies, and other objects within this boundary. The size of this sphere is not decided by technology or telescopes, but by one simple rule of nature: the speed of light. Since nothing can move faster than light, there is a maximum distance from which information can ever reach us. This invisible wall is called the particle horizon. Anything beyond it is forever hidden, because its signals have not yet, and may never, arrive at Earth. If we assume the universe looks the same in every direction, then the edge of this observable sphere is at the same distance no matter which way we look. In other words, every observer in the universe has their own version of an observable universe, centered around them. Ours is just one example among countless others, and in many cases these spheres may overlap. According to scientific calculations, the current distance to the farthest matter we can observe, such as the point where the cosmic microwave background radiation first formed, is about 14 billion parsecs, which equals around 46 billion light-years. The very edge of what we can observe is just a little farther away, around 14.3 billion parsecs, or about 46.6 billion light-years. This makes the radius of the observable universe roughly 46.5 billion light-years. By using the critical density of the universe and this enormous diameter, scientists estimate that all the ordinary matter in the universe weighs about 1.5 times 10 to the power of 53 kilograms. In November of the year 2018, astronomers also reported that the background glow from all distant galaxies, called the extragalactic background light, contained about 4 times 10 to the power of 84 photons. But the story does not end here. The universe is not only expanding, it is expanding faster and faster. Because of this, everything outside our local group of galaxies will, over time, appear to stop moving and freeze in place. The light from these distant objects will stretch into longer, redder wavelengths and become fainter until it vanishes from our view. For example, objects with a redshift value between 5 and 10 can only be observed for about 4 to 6 billion years before they slip away beyond our reach. In addition, any light emitted today from galaxies located farther than about 19 billion parsecs, or 62 billion light-years, will never make it to Earth at all. The total size of the universe is unknown. It might even be infinite. Many regions are simply too far for their light to have reached us since the Big Bang. In the far future, as time passes, light from some of those distant areas may finally arrive, adding new regions to our observable universe. Yet there is a limit to this process. Because of the ever-increasing expansion, some galaxies are moving away from us faster than light itself. This effect, first described by Hubble's law, means that many of those galaxies will never be seen, no matter how long we wait. To explain this acceleration, scientists propose the existence of something mysterious called dark energy, which acts as a repelling force in space. If dark energy remains constant and keeps driving the universe apart at an accelerating rate, there will always be a limit beyond which objects can never be seen, even in the infinite future. This boundary is known as the future visibility limit. Currently, it is estimated at 19 billion parsecs, or 62 billion light-years. This means that the total number of galaxies humanity could ever observe, even across all of time, is only a little more than twice the number we can see today. However, even though more galaxies may technically become visible, their light will be stretched so much by cosmic expansion that they will fade into invisibility. A galaxy within our observable universe today might send us signals from its early years, perhaps from just 500 million years after the Big Bang, but later signals, say from when it was 10 billion years old, might never reach us because of this expansion. This leads to the idea of a cosmic event horizon. The current distance to this horizon is about 16 billion light-years. Any event happening closer than this may still send signals that will eventually reach Earth, even if it takes billions of years. But events happening farther away than this horizon will never be seen by us, no matter how long we wait. The region inside this cosmic event horizon can be called the reachable universe. Galaxies within it could, in theory, be reached if one could travel at the speed of light. Galaxies beyond it, however, will remain forever unreachable. Interestingly, the numbers line up neatly. The future visibility limit of about 62 billion light-years is exactly the sum of the current visibility limit of about 46 billion light-years and the reachable limit of about 16 billion light-years. This shows the delicate balance between what we can see now, what we could ever reach, and what will remain forever beyond our sight. In both everyday science writing and professional research in cosmology, the word universe is often used to mean the observable universe. This is not just a casual mistake. It makes sense, because we can never directly observe or study any part of the universe that has no way of affecting Earth. Light and other signals from those faraway regions can never reach us, so they remain permanently hidden. Even so, many strong and credible scientific theories suggest that the total universe is far larger than just the observable part. There is no evidence at all to suggest that the outer edge of the observable universe is the true boundary of the universe itself. In fact, most accepted models in cosmology do not propose that the universe has a physical edge at all. Some theories even suggest that the universe could be finite in size but still have no boundaries, similar to how the two-dimensional surface of a sphere is finite in area but has no edges. If you travel along the surface of a sphere, you never fall off an edge, even though the surface is not infinite. In the same way, the universe could be finite but without a sharp edge or border. It is very possible that the galaxies we can see inside the observable universe are only a tiny fraction of the galaxies that exist in the entire universe. According to the theory of cosmic inflation, which was first proposed by physicists Alan Guth and Dimitri Kazanis, the universe expanded incredibly fast in its earliest moments. If inflation began about 1/10 million trillion trillionth of a second after the Big Bang, and if the size of the universe before this inflation was about the same as the speed of light multiplied by its age at that time, then today the whole universe would be at least 1.5 times 10 to the power of 34 light-years across. That makes it at least 3 times 10 to the power of 23 times larger than the radius of the observable universe. Interestingly, if the universe is finite but unbounded, it could actually be smaller than the observable universe. In such a case, what we see as very distant galaxies might not really be separate galaxies at all. They could instead be duplicate images of nearby galaxies. This would happen because light could travel all the way around the universe, arriving at us from different directions. Testing this idea is very difficult. different images of the same galaxy would show it at different times in its history because light takes time to travel, and so the images could look very different from one another. In the year 2011, a study by Bielowicz and colleagues used data from the 7-year observations of the Wilkinson Microwave Anisotropy Probe, also known as WMAP. They tried to measure the last scattering surface, which is the point in time when the universe first became transparent to light, allowing photons to move freely. Their analysis suggested that the minimum possible diameter of this surface was about 27.9 gigaparsecs, which equals roughly 91 billion light-years. This result came from a method called the matching circle analysis, but not everyone agrees with their findings, and it has been debated in the scientific community. At present, the comoving distance from Earth to the edge of the observable universe is about 14.26 gigaparsecs, which is equal to about 46.5 billion light-years, or about 4.4 times 10 to the power of 26 meters in every direction. That means the observable universe is like a sphere centered on Earth, with a diameter of about 28.5 gigaparsecs, which equals about 93 billion light-years, or about 8.8 times 10 to the power of 26 meters. If space is roughly flat, which means it behaves like Euclidean space in geometry, then this corresponds to a comoving volume of about 1.22 times 10 to the power of 4 cubic gigaparsecs, which equals about 4.22 times 10 to the power of 5 cubic billion light-years, or about 3.57 times 10 to the power of 80 cubic meters. It is important to remember that these distances are measured in cosmological time, meaning they are based on the present size of the universe. They are not the same as the distances that existed when the light first left those objects. For example, the cosmic microwave background radiation we observe today was emitted when the universe was only about 380,000 years old. That moment is known as photon decoupling, the time when the universe cooled enough for light to move freely without being constantly scattered by matter. This happened about 13.8 billion years ago. The light we now see from that event was released by matter that later condensed into galaxies. Today, those galaxies are calculated to be about 46 billion light-years away from us. If we try to estimate the distance to that same matter, back when the light was first emitted, we need to use the Friedmann-Lemaitre-Robertson-Walker metric, which is the standard mathematical model of the expanding universe. In this model, light from the early universe is stretched out by cosmic expansion, which we see as redshift. According to the results from WMAP combined with other data, the redshift of photon decoupling is about 1091.64, with a margin of error of less than 1/2. This means that the scale of the universe back then was only about 1 divided by 1092.64 of its current size. So, if the matter that emitted the oldest cosmic microwave background photons is now about 46 billion light-years away, at the time of decoupling it was only about 42 million light-years away. Another way of thinking about this is through the concept of light travel distance. This is the distance light could have travelled since the Big Bang, moving at the speed of light for the entire age of the universe. Since the universe is about 13.8 billion years old, the light travel distance is 13.8 billion light-years. This is the distance that a photon, emitted shortly after the Big Bang, would have travelled to reach us today. But because space itself has been expanding all along, the true distance to the source of that photon is much greater. In fact, space-time is curved and constantly stretching, so the path light takes through it does not correspond to a single fixed distance at any one moment in time. The part of the cosmos that we can actually observe is unimaginably huge and filled with more wonders than our minds can easily grasp. Astronomers estimate that there may be as many as 2 trillion galaxies in this observable universe. Inside those galaxies could be around 10 to the power of 24 stars. That is a 1 followed by 24 zeros. To put this in perspective, there could be more stars, and perhaps even more Earth-like planets, than all the grains of sand on every beach of planet Earth combined. Some estimates are more modest, suggesting hundreds of billions of galaxies instead of trillions, but even those lower numbers are staggeringly large. If the theory of cosmic inflation is right, and the universe expanded by more than 60 E-folds in its earliest moments, then the entire universe could contain a number of stars so vast it is nearly impossible to imagine. Possibly as many as 10 to the power of 100 stars, a number that dwarfs anything we normally deal with. When scientists try to calculate the amount of ordinary matter in the observable universe, They work with an estimated mass of about 1.45 times 10 to the power of 53 kilograms. To make the calculation simple, imagine all of this matter being made of hydrogen atoms, which make up about 74% of all the atoms in our own Milky Way galaxy by mass. By dividing the total mass of this ordinary matter by the mass of a single hydrogen atom, astronomers arrive at a result of about 10 to the power of 80 atoms. This number is sometimes called the Eddington number, and it gives us a sense of just how many building blocks of matter fill the observable cosmos. The quoted mass of the observable universe is usually around 10 to the power of 53 kilograms. Here, when scientists speak of mass, they are referring only to ordinary matter, also called baryonic matter. This includes the gas and dust that fill the space between stars, known as the interstellar medium, and the thin matter spread between galaxies, called the intergalactic medium. This number does not include dark matter or dark energy, which together make up most of the universe but remain invisible and mysterious. The estimated value comes from calculations based on something called the critical density, which is the energy density at which the universe would be perfectly balanced, flat in shape. Without dark energy, this critical density would mark the point where the universe hovers between endless expansion and eventual collapse. Ordinary matter makes up only a small fraction of the total. Measurements from the European Space Agency's Planck satellite show that baryonic matter is just about 4.8% of the critical density. That equals a density of about 4.08 times 10 to the power of negative 28 kilograms per cubic meter. To figure out how much mass this represents, scientists multiply this density by the total volume of the observable universe. Since the universe has been expanding for about 13.8 billion years, the comoving radius of the observable part is now roughly 46.6 billion light-years. With that radius, the volume works out to about 3.58 times 10 to the power of 80 cubic meters. Multiplying this by the density gives a total mass of about 1.46 times 10 to the power of 53 kilograms for all ordinary matter. Over the decades, sky surveys that scan the heavens across different wavelengths of light, including radio waves such as the 21 centimeter hydrogen emission, have helped us map the distribution of galaxies and other cosmic structures. What emerges is a vast hierarchy. Stars gather into galaxies cluster into groups, which then form larger structures called clusters and superclusters. These in turn stretch out into sheets, walls, and thread-like filaments separated by enormous empty regions called voids. Together, this arrangement is often referred to as the cosmic web, a gigantic foam-like pattern on the larger scales. Before the year 1989, many astronomers thought that galaxy clusters were the largest structures in existence, scattered somewhat evenly across the universe. But discoveries from the early 1980s onward began to reveal far greater patterns. In the year 1983, astronomer Adrian Webster identified the Webster Large Quasar Group, or LQG, which contained 5 quasars. This was the first time astronomers realized that objects could be connected on such a large scale. In the year 1987, Robert Brent Tully identified the Pisces-Cetus supercluster complex, the vast galaxy filament that includes our own Milky Way galaxy. It measures about 1 billion light-years across. That same year, scientists discovered the Giant Void, an enormous region with far fewer galaxies than normal, stretching about 1.3 billion light-years across. In the year 1989, Margaret Geller and John Huchra discovered the famous Great Wall, a colossal sheet of galaxies more than 500 million light-years long, 200 million light-years wide, and about 15 million light-years thick. Finding this structure was challenging because it required knowing the three-dimensional positions of galaxies, which meant combining both their locations on the sky and their distances measured from redshifts. Only 2 years later, in 1991, Roger G. Clowes and Louis E. Campusano discovered another large quasar group, the Clowes-Campusano LQG, stretching 2 billion light-years at its widest point. At the time, it was the largest known structure in the universe. In April of the year 2003, astronomers found another immense feature, the Sloan Great Wall. Then, in August of the year 2007, a possible supervoid was detected in the constellation Eridanus. This region overlaps with a cold patch in the cosmic microwave background radiation known as the CMB cold spot. For this void to explain the cold spot, it would need to be improbably large, possibly as wide as 1 billion light-years, almost matching the giant void itself. Another striking large-scale structure is the SSA-22 protocluster, a huge collection of galaxies and enormous gas bubbles spanning about 200 million light-years. In the year 2011, astronomers found a large quasar group named Ussat 11 that measures about 2.5 billion light-years across. Just 2 years later, on the 11th of January in the year 2013, another quasar group was discovered, the huge LQG, an astonishing 4 billion light-years across, making it at that time the largest known structure in the universe. But discoveries did not stop there. In November of the same year, astronomers found something even bigger, the Hercules Corona Borealis Great Wall, a structure about twice as large as the huge LQG. This vast feature was identified by mapping the distribution of gamma-ray bursts across the sky. In the year 2021, the American Astronomical Society announced the detection of the Giant Arc, a graceful, crescent-shaped chain of galaxies spanning about 3.3 billion light-years in length. It lies around 9.2 billion light-years away from Earth in the constellation Boötes, revealed through the data of the Sloan Digital Sky Survey. The observable universe, with all of these galaxies, stars, atoms, and colossal structures, is beyond anything our everyday experiences can prepare us for. Even the numbers used to describe it stretch far past the limits of our imagination. It is a place of endless variety, order on enormous scales, and mysteries that continue to unfold with each new discovery. The phrase, "the end of greatness," is sometimes used to describe a special scale in the universe, one that is about 100 megaparsecs across, that is roughly 300 million light-years. On this scale, the clumpy and uneven look of the universe, with its crowded groups of galaxies and long filaments, begins to smooth out. Instead of being bumpy and irregular, it becomes evenly spread out in all directions, just as the cosmological principle says it should. Scientists measure this lumpiness by calculating something called a fractal dimension, which tells them how uneven or structured the universe looks when viewed at different scales. On smaller scales, surveys show great chains of galaxies, giant superclusters, and cosmic filaments. But when one zooms out to the scale of the end of greatness, all those patterns begin to blur together until the universe looks smooth and uniform. Astronomers could not truly confirm this until the 1990s, when large redshift surveys were finally finished and gave us a clearer picture of the cosmos on this immense scale. Another key clue to the universe's large-scale structure is something called the Lyman Alpha Forest. This forest is not made of trees but of many thin dark lines seen in the light spectra of quasars. Each of these lines marks where light has passed through enormous sheets of hydrogen gas floating between galaxies. Over time, these sheets collapse into cosmic filaments, feeding growing galaxies at the points where the filaments intersect or become dense. In the year 2019, astronomers from the Riken Cluster for Pioneering Research in Japan and Durham University in the United Kingdom detected light from part of this hidden web. What they saw was a glowing region of gas, lit up like a lantern by a cluster of baby galaxies forming inside it, shining as cosmic flashlights. This was one of the first clear pieces of evidence of the vast cosmic web itself. Then, in the year 2021, an international team led by Roland Bacon from the Centre de Recherche Astrophysique de Lyon in France reported another exciting discovery. They observed faint, widespread Lyman alpha emissions stretching across scales of between 2.5 and 4 co-moving megaparsecs, which trace several long cosmic filaments outside the crowded hubs of galaxy clusters. For the first time, astronomers could directly see threads of the cosmic web glowing softly in deep space. But scientists must be careful when describing cosmic structures, because they do not always appear as they truly are. One reason is gravitational lensing. Massive objects, like galaxies or galaxy clusters, bend the fabric of space-time around them. This warping bends light rays passing nearby, making distant objects appear in the wrong place, or even stretched and multiplied. While this can confuse observations, it can also help, since strong gravitational lensing sometimes acts like a natural magnifying glass, making it possible to detect galaxies that would otherwise be too faint or too far away. Weak lensing, by comparison, slightly distorts the overall picture of the universe's structure. Distances can also be misleading if astronomers rely only on redshift. For instance, galaxies that sit behind a massive cluster are pulled toward it by gravity. This attraction changes the way their light is shifted, making them appear closer or farther than they really are. The result is that the cluster's shape looks oddly squashed when plotted in redshift space. Inside the cluster itself, galaxies move randomly around the center. When this random motion is turned into redshift data, the cluster appears stretched into a long thin chain pointing directly at Earth. At the very heart of the Hydra Centaurus supercluster lies another mystery, the Great Attractor discovered in the year 1986. This is a gravitational anomaly so massive that it pulls galaxies across hundreds of millions of light-years. Although these galaxies follow Hubble's law and are redshifted, meaning they are receding from us, their motions are altered in such a way that the hidden mass of the Great Attractor becomes obvious. It is thought to be as heavy as tens of thousands of galaxies combined. The Great Attractor lies somewhere between 150 million and 250 million light-years away, in the direction of the Hydra and Centaurus constellations. Around it lie many huge old galaxies, some colliding with neighbours and others blasting out powerful radio waves. In the following year, 1987, astronomer R. Brent Tully from the University of Hawaii's Institute for Astronomy made another bold claim. He described a gigantic structure he called the Pisces-Cetus supercluster complex, stretching about 1 billion light-years in length and 150 million light-years across. He suggested that even our own local supercluster sits inside this immense cosmic wall. The most distant known astronomical object today is a galaxy called MOAM Z14, found at a redshift of 14.44. Earlier, in the year 2009, scientists discovered a spectacular gamma-ray burst named GRB 090423, with a redshift of 8.2. This meant the collapsing star that created it exploded when the universe was only about 630 million years old. The flash of this burst reached us after a journey of around 13 billion years. Newspapers at the time reported its distance as about 13 billion light-years, though a more exact figure given was 13.035 billion light-years. However, this number refers to light travel distance and how long the light took to reach us, not the actual proper distance used in Hubble's law or in defining the size of the observable universe. According to cosmologist Ned Wright, this is a misleading way to measure distance. If we use proper distance instead, a redshift of 8.2 corresponds to about 9.2 gigaparsecs, or around 30 billion light-years. Ultimately, there is a limit to how far into the cosmos we can ever see. These limits are set by cosmological horizons. The most famous of these is the particle horizon, which marks the maximum distance we can observe, given the universe's finite age. Beyond it, light has not had enough time to reach us. Other horizons exist as well, one that defines how far we may see in the future as space continues to expand. The optical horizon that comes from the surface of last scattering when light first became free to travel, and even horizons for the earliest neutrinos and gravitational waves. These boundaries remind us that no matter how powerful our telescopes become, there are parts of the universe forever beyond our reach. The cosmic horizon is a phrase used to describe the most distant boundary of the universe that we can possibly observe. It is the farthest edge from which light, or any form of information carried by light, has had enough time to reach us since the very beginning of the cosmos. That beginning is what we call the Big Bang, which took place around 13.8 billion years ago. If we think of the universe as a grand stage that has been unfolding since that first moment, then the cosmic horizon is like the farthest row of seats from which we can still see what is happening. Beyond that, we know the play continues, but the signals have not yet reached us, so it remains hidden from our eyes and instruments. At first glance, one might assume that the cosmic horizon should simply be 13.8 billion light-years away from us, since light has had 13.8 billion years to travel. A light-year is the distance that light can cover in 1 year, and since light moves incredibly fast, almost 300,000 kilometers every second, a single light-year stretches to nearly 10 trillion kilometers. Multiplying such a huge distance by 13.8 billion gives us an unimaginable figure. But the universe is not static. It is not a still, unchanging space through which light travels. The universe has been expanding ever since the Big Bang, and what makes things even more complicated is that this expansion is not slowing down, it is accelerating. This expansion stretches space itself, carrying galaxies farther apart like raisins carried apart in dough that is rising in an oven. This stretching means that the light we see from the earliest times has been travelling through a fabric that has grown larger and larger. Because of this expansion, the actual size of the observable universe, the portion of the universe from which we can receive light, is far greater than just 13.8 billion light-years. Scientists, by carefully studying the expansion and the speed at which galaxies move away from each other, have calculated that the radius of the observable universe is about 46.5 billion light-years in every direction. That means that from our vantage point here on Earth, if we look in any direction, north, south, east, or west, the farthest galaxies we can detect lie around 46.5 billion light-years away. Since this is a radius, the full observable universe stretches across a diameter of about 93 billion light-years. To put this into perspective, if you could somehow draw a straight line from one edge of the observable universe, passing through Earth, all the way to the opposite edge, the total length of that line would be roughly 93 billion light-years. This is astonishing, because it shows that the universe we can actually observe is much larger than the simple age of 13.8 billion years would suggest. The reason lies in the stretching of space itself, which has carried galaxies away even as their light was journeying towards us. In other words, some of the galaxies we can now see as faint specks of light were much closer when the light left them billions of years ago, but the relentless expansion of the cosmos has since carried them much farther away. By the time their light finally reaches our telescopes, those galaxies are no longer at the place where the light was originally emitted. They are now much farther out. So, while we are witnessing their ancient light, the galaxies themselves are now situated tens of billions of light-years from us. To imagine this in a simpler way, picture a ship sailing away from a lighthouse at night. The lighthouse beam shines across the water, and the ship moves farther and farther away. The light that was emitted at a particular moment still travels across the sea and eventually reaches the ship, even as the ship continues to drift further away. When the beam finally catches the ship, the vessel is no longer at the position where it was when the light first began its journey. Instead, it is much farther from the lighthouse. Similarly, galaxies in the expanding universe continue to recede while their ancient light travels through space to reach us today. The immensity of 46.5 billion light-years as a radius and 93 billion light-years as a full diameter is difficult to picture. The human mind struggles with distances so vast that even the numbers lose their meaning. Let us try to imagine by comparing it to something closer to our experience. Our own Milky Way galaxy, which is the vast system of stars, gas, dust, and dark matter to which our solar system belongs, is around 100,000 light-years across. That means that the observable universe is almost 1,000,000 times larger than the Milky Way. If the Milky Way were reduced to the size of a single grain of sand, the observable universe would be a sphere stretching many kilometers across. Within that enormous sphere, there are not just countless stars but trillions of galaxies, each filled with hundreds of billions of stars and likely even more planets. The numbers swell beyond comprehension, yet they all reside within this visible bubble defined by the cosmic horizon. The concept of the cosmic horizon also carries an important implication. There are regions of the universe beyond it that we can never see, no matter how long we wait. The reason is that space itself is expanding faster than the speed of light at great distances. Light from galaxies that lie beyond the cosmic horizon will never have the chance to reach us, because the fabric of space is stretching too quickly, pulling them away faster than their light can cross the gap. In this sense, the cosmic horizon is a kind of ultimate boundary for human observation. Beyond it, the universe may continue endlessly, filled with structures, galaxies, and wonders, but they remain forever hidden from us. We know that something exists out there, but we can never directly observe it. It is humbling to think about the fact that we are surrounded by this invisible horizon. Everywhere we look, we see into the past. The light from our sun, which is about 8 minutes away at the speed of light, shows us the sun as it was 8 minutes ago. The light from the nearest star outside our solar system, Proxima Centauri, takes about 4 years to reach us, so when we gaze upon it, we are looking 4 years into the past. The light from the Andromeda Galaxy, our closest large galactic neighbour, takes about 2.5 million years to arrive. That means we see Andromeda not as it is today, but as it was 2.5 million years ago, when early humans were just beginning to appear on Earth. As we look deeper into the sky, we reach billions of years back in time, until we approach the cosmic horizon, where we see the faint afterglow of the Big Bang itself, known as the cosmic microwave background radiation. That glow has travelled across the universe for nearly the entire history of time to reach us, carrying with it a snapshot of the infant universe. This backward glance into cosmic history reveals a strange truth. The farther we look, the younger the universe appears. When we look at nearby stars, we're seeing them as they were in the recent past. When we look at distant galaxies, we're observing them as they were billions of years ago, when the universe was still young. At the very edge, the cosmic horizon shows us the universe in its infancy, filled not with galaxies and stars, but with a hot, dense plasma glowing with primordial light. That ancient light, stretched into microwaves by the expansion of space, forms a faint but uniform background across the sky, serving as a reminder of our origins. The notion that the observable universe is 93 billion light-years across might sound contradictory at first, since the universe itself is only 13.8 billion years old. Yet this is resolved by remembering that the universe is not a static container, but an expanding fabric. The distances we speak of are not fixed, but stretch as space grows. What we measure today as 46.5 billion light-years in radius is the current distance to those galaxies, not the distance when their light was emitted. When the light began its journey billions of years ago, those galaxies were much closer, perhaps only a few billion light-years away. Over time, as the light travelled, the galaxies were carried ever farther out by cosmic expansion. This is why the size of the observable universe is much greater than the simple age of the cosmos, multiplied by the speed of light. It is also remarkable to consider that what we call the observable universe is only the part of the cosmos that is visible to us. Beyond the cosmic horizon, the universe could extend endlessly. Some theories suggest it is infinite, with no boundary at all. Others suggest that it may curve back upon itself, forming a finite but unbounded shape, like the surface of a sphere in higher dimensions. Whatever the case, the observable universe is only a small window onto the whole. It is like standing in a vast forest and seeing only the trees nearby, while the rest stretches on endlessly beyond the mist. The discovery of the accelerating expansion of the universe came in the late 1990s, when astronomers observed distant exploding stars called supernovae. These cosmic beacons revealed that galaxies were not just moving apart, but doing so at an ever-increasing speed. The cause of this acceleration remains one of the greatest mysteries in physics, attributed to a strange unseen force known as dark energy. This mysterious component seems to make up about 70% of the universe, pushing galaxies apart with increasing strength. Because of dark energy, the cosmic horizon is not fixed but changes with time. In the distant future, more and more galaxies will slip beyond it, disappearing from our view forever. The observable universe will gradually grow emptier as cosmic expansion accelerates. This reality means that the night sky we enjoy today is richer and more crowded than the skies future generations will see billions of years from now. Slowly, galaxies that are now visible at the edge of the horizon will fade away, carried beyond the limit of observation. The cosmic horizon will become not just a boundary of our past, but a boundary of our future vision as well. In the very distant future, observers in our galaxy may find themselves surrounded by a lonely sky, with only the nearest galaxies still visible and all evidence of the broader universe hidden beyond the horizon. The vastness of the observable universe we see today is a temporary gift, a window that will not remain open forever. The numbers themselves are staggering, but what they reveal is even more profound. A radius of 46.5 billion light-years means that the observable universe contains not only countless galaxies, but also a timeline of cosmic history stretching all the way back to the beginning. Every patch of sky, no matter how small, holds within it thousands of galaxies if we look deep enough with powerful telescopes. Astronomers have pointed the Hubble Space Telescope at what appeared to be an empty patch of sky, no larger than a grain of sand held at arm's length, and found thousands of galaxies within it. If such a tiny region contains so many, then the entire sky, multiplied by the scale of the cosmic horizon, holds trillions upon trillions of galaxies. The expansion of the universe means that the distances between galaxies and other parts of the cosmos that are not held together by gravity are increasing as time goes on. This is not like a balloon inflating into some empty space that exists outside of it. Instead, it is an expansion of space itself, an intrinsic stretching of the very fabric of the cosmos. There is no outside into which the universe is expanding. To any observer, no matter where they are in the universe, it appears that nearly all galaxies are moving away. Only the closest galaxies, which are bound together by gravity, do not drift apart. What makes this even more fascinating is that the farther away a galaxy is, the faster it seems to be receding from the observer. This relationship is not random. It follows a pattern. On average, galaxies that are twice as far away move away twice as quickly. Now, it is true that nothing can travel faster than the speed of light when measured locally, but this rule applies only to objects moving through space. When it comes to the stretching of space itself on a cosmic scale, entire galaxies can appear to recede from us faster than light, and this does not break the laws of physics. The discovery that the universe is expanding was one of the most important scientific findings of the 20th century. It did not come from one single moment or one scientist, but from a series of theoretical insights and careful observations during the 1920s. Since then, the idea of cosmic expansion has become one of the central pillars of cosmology, the branch of science that studies the origin, structure, and fate of the universe. Enormous scientific projects have been devoted to studying this expansion, trying to measure it with greater and greater accuracy and to understand what it means for the future of the cosmos. The expansion of the universe is also at the heart of Big Bang cosmology. Within the framework of Albert Einstein's theory of general relativity, scientists describe this expansion mathematically using what is known as the Friedmann-Lemaitre-Robertson-Walker metric. The standard model of cosmology today, called the lambda-cold dark matter model, tells us that the rate of expansion has not been the same throughout all of cosmic history. It has changed depending on what the universe contained at different times: radiation, matter, dark matter, or the mysterious force called dark energy. In the very earliest moments, there was a period of unimaginable growth called cosmic inflation. In less than a trillionth of a second, more precisely about 10 to the power of negative 32 seconds after the Big Bang, the universe suddenly expanded by a factor of at least 10 to the power of 26 in every direction. This was a mind-bogglingly fast stretching that set the stage for everything that would follow. After that, the rate of expansion slowed down dramatically, allowing matter to clump together into stars, galaxies, and eventually planets. For billions of years, expansion continued at this slower pace. But then, about 9.8 billion years after the Big Bang, which is roughly 4 billion years ago, the expansion began to speed up again. It is still accelerating today, driven by what scientists call dark energy. In the simplest models, this dark energy behaves like a cosmological constant, a kind of built-in energy of space itself. If this is correct, dark energy will dominate the future of the universe, causing galaxies to drift ever farther apart. The concept of an expanding universe is not easy to grasp. Because of this, many misunderstandings have arisen about what it means, where it came from, and what effects it has. But step by step, scientists built up the evidence. Between the years 1912 and 1914, the astronomer Vesto Slipher made a remarkable discovery. Light from faraway galaxies was redshifted, meaning its wavelengths were stretched. This stretching was later interpreted as a sign that those galaxies were moving away from Earth. In the year 1922, the Russian physicist Alexander Friedmann took Einstein's field equations of general relativity and showed, with mathematics, that the universe could not be static but had to be expanding. The key observational proof of cosmic expansion came to be known as Hubble's law, though today it is also sometimes called the Hubble-Lemaitre law. The naming is debated because several scientists played important roles. In the year 1924, the Swedish astronomer Knut Lundmark presented observational evidence that pointed toward expansion. His results, impressively accurate for the time, were based on measuring galaxy sizes and estimating the distance to the Andromeda galaxy. However, because these measurements were not firmly proven then, his conclusions did not receive full recognition. In 1927, the Belgian priest and physicist Georges Lemaitre solved Einstein's equations and applied them to observational data collected by Slipher and Edwin Hubble. He proposed a simple linear relationship. The farther a galaxy was, the faster it receded. Just 2 years later, in 1929, Edwin Hubble confirmed this relationship by using multiple independent methods. His results firmly established what we now call the law of cosmic expansion. Interestingly, Hubble himself did not initially link this relationship directly to the expansion of space. His estimate of the rate of expansion, now called the Hubble constant, was also far too large, off by about a factor of 7. Even so, his work ignited tremendous interest in earlier theories and inspired scientists to refine measurements with increasing precision. In the 1940s, astronomer Walter Baade recalculated distances to galaxies, doubling the estimated size of the known universe. For much of the second half of the 20th century, scientists debated the value of the Hubble constant, with estimates ranging between 50 and 90 kilometers per second per megaparsec. On the 13th of January in the year 1994, NASA announced that repairs to the main mirror of the Hubble Space Telescope had been completed. This allowed the telescope to produce much sharper images, dramatically improving the accuracy of cosmological measurements. That same year, Wendy Friedman led what became known as the Hubble Key Project. Her team studied the Virgo cluster of galaxies and obtained a value for the Hubble constant of about 80, plus or minus 17, kilometers per second per megaparsec. Later in 1994, Adam Rees and his colleagues improved methods for measuring the brightness of Type Ia supernovae, further reducing errors. Their analysis suggested a value of 67, plus or minus 7. These results were consistent with later measurements that used Cepheid variable stars to calibrate distances, which gave an estimate of 73, plus or minus 7. By the year 2003, David Spergel and his team analysed the cosmic microwave background using data from the Wilkinson Microwave Anisotropy Probe WMAP satellite. Their results showed an expansion rate of about 72, plus or minus 5 kilometers per second per megaparsec, remarkably close to values measured from galaxies in our cosmic neighbourhood. When we look out into the vastness of space in every direction, astronomers notice something remarkable. Distant galaxies are moving away from us. Not only that, but the farther a galaxy is from Earth, the faster it seems to recede. This discovery, known as Hubble's law, tells us that the universe is not static. It is expanding. Imagine the universe as a gigantic, stretching balloon with galaxies embedded on its surface. As the balloon inflates, every galaxy drifts away from every other galaxy. This expansion is not random or lopsided. Observations reveal that, on the larger scales, the universe looks remarkably uniform, no matter where you are or in which direction you look. Scientists describe this property using two terms. The universe is homogeneous, meaning it has roughly the same composition and structure everywhere, and isotropic, meaning it looks the same in all directions. Because of this uniformity, the stretching of the cosmos is happening evenly throughout space today. In practical terms, the distance between any two galaxies grows steadily over time, with every pair moving apart by the same relative factor. Mathematically, this uniform expansion is captured by a simple relationship between a galaxy's velocity of recession and its distance from us. The reason the universe is expanding can be traced back to its earliest moments. From the very beginning, the contents of the universe, matter, radiation, and energy, were flying apart. Gravity, the force that pulls matter together, works to slow down this expansion over time. Yet, the universe's average density is not high enough to stop the expansion completely. More intriguingly, in recent cosmic history, a mysterious phenomenon called dark energy appears to be pushing space apart even faster, accelerating the expansion rather than slowing it. To describe this growth more precisely, cosmologists use a concept called the scale factor, often written as A. This number measures how distances in the universe change over time. By convention, the scale factor today is set to 1, corresponds to the present moment. Because the universe has been expanding, the scale factor was smaller in the past and will grow larger in the future. If we trace the universe backward in time using modern cosmological models, there comes a moment when the scale factor reaches 0. This point corresponds to the birth of the universe itself, known as the Big Bang, which occurred approximately 13,787,000,000 years ago, plus or minus 20 million years. Looking ahead, if expansion continues forever, the scale factor could grow without limit. However, it is also theoretically possible that the universe could eventually stop expanding and begin to shrink, causing the scale factor to decrease over time. The scale factor is a central part of the mathematical description of the universe, encoded in the Friedman-Lemaitre-Robertson-Walker (FLRW) metric. Its behavior over time is governed by the Friedman equations, which connect the expansion of space to the universe's contents. One of these equations shows how different forms of energy and matter influence the acceleration or deceleration of expansion. In this framework, G represents the gravitational constant, R is the energy density of everything in the universe, P is pressure, C is the speed of light, and L is the cosmological constant. A positive energy density tends to slow expansion down, while positive pressure also contributes to deceleration. Interestingly, if the pressure is sufficiently negative, the universe can accelerate in its expansion. This is what is thought to happen with dark energy. It behaves like a fluid with negative pressure, causing space to expand faster over time. Ordinary matter, like stars and planets, has negligible pressure compared to its energy density, while a gas of ultra-relativistic particles such as light exerts positive pressure equal to 1/3 of its energy density times the speed of a light squared. Even though negative pressure fluids, like dark energy, have not been directly observed in the laboratory, their effects are inferred from astronomical observations. Galaxies are moving apart more rapidly than expected from matter alone, and the universe's large-scale geometry suggests the presence of this mysterious, invisible component, shaping the cosmos in ways we are only beginning to understand. In a universe that is constantly expanding, it often becomes helpful to study how structures, like galaxies, clusters, and cosmic filaments, change over time while factoring out the expansion itself. This is where the concept of co-moving coordinates becomes very useful. Co-moving coordinates are a kind of coordinate system designed to expand alongside the universe. In other words, as the universe grows larger, these coordinates stretch in proportion to the cosmic scale factor, which is a measure of the universe's size at any given time. If an object is only moving along with the general expansion of the universe, what astronomers call the Hubble flow, and has no other motion of its own, then in co-moving coordinates, it appears completely stationary. Essentially, co-moving coordinates are the spatial coordinates used in the Friedmann-Lemaitre-Robertson-Walker (FLRW) metric, which is the standard way to describe the geometry of the expanding universe. Even though the universe is fundamentally a four-dimensional space-time, 3 dimensions of space and 1 of time, there is a natural way to choose a 3-dimensional slice of space that is consistent with the cosmological principle, which states that the universe is roughly the same everywhere and in every direction. These special 3-dimensional surfaces are called co-moving synchronous spatial surfaces, and they are the surfaces on which observers who are at rest with respect to the co-moving coordinates would agree on the age of the universe. In a universe governed purely by special relativity, these surfaces would form curved shapes called hyperboloids, because the phenomenon of time dilation causes the clocks of observers moving very quickly relative to us to run slower. Therefore, the spatial surfaces must bend forward in time over long distances to account for this effect. But in general relativity, which accounts for gravity, the shape of these comoving surfaces can be influenced by gravitational effects. Observations today suggest that the universe is geometrically flat on large scales, meaning, for example, that the angles of a very large cosmic triangle would sum to exactly 180 degrees. Because the universe has been expanding for a finite amount of time, light and other particles can only travel a limited distance. The comoving distance that a particle could have travelled since the beginning of the universe is called the particle horizon. Everything that lies within this horizon makes up the observable universe, which is all the part of the cosmos we could ever hope to see, even with perfect instruments. Modern cosmology also introduces the idea of dark energy, a mysterious form of energy that appears to dominate the universe today and is thought to act like a cosmological constant. If this is correct, then the particle horizon approaches a finite size even in the infinite future. This means there is a hard limit on how much of the universe we will ever be able to observe. Some galaxies and systems exist beyond what is called the cosmic event horizon. Their light will never reach us because the repulsive effect of dark energy pushes them away faster than light can travel. When scientists study the growth of structure in the universe, they often encounter a natural scale called the Hubble horizon. This is essentially a limit beyond which gravitational effects cannot influence a region quickly enough to alter its behavior. Perturbations or irregularities in the density of the universe that are much larger than the Hubble horizon do not evolve dynamically because gravity has no time to affect them. On the other hand, smaller perturbations behave in a way that can be largely described by Newtonian gravity, which is the familiar gravity of everyday experience. Light, and especially photons, are affected by the expansion of space in a phenomenon known as cosmological redshift. While this redshift is often explained as the stretching of wavelengths due to the expansion of space itself, it can also be understood as a type of Doppler effect, similar to how a siren sounds lower in pitch as it moves away from you. Every object also has what is called a peculiar velocity, which measures how fast it is moving relative to the average Hubble flow of the surrounding universe. This velocity tells us how much an object deviates from simply drifting along with cosmic expansion. As the universe grows, the peculiar velocities of slow-moving, non-relativistic particles gradually decrease in proportion to the expansion, which is a result of a kind of self-sorting process. Particles moving slightly faster than their neighbours eventually settle into the flow of surrounding matter. For all particles, whether fast-moving or slow, their peculiar momentum diminishes roughly in inverse proportion to the scale factor. The cooling of the universe is directly linked to this process. As peculiar momenta decay, the universe's contents lose energy, which manifests as a drop in temperature, a process known as adiabatic cooling. The temperature of highly energetic, fast-moving particles, ultra-relativistic fluids, such as radiation including the cosmic microwave background, decreases roughly in inverse proportion to the scale factor. In simpler terms, if the universe doubles in size, the temperature of this radiation halves. For non-relativistic matter, like cold gas or dust, the temperature falls even faster, roughly in proportion to the inverse square of the scale factor. As space stretches, the matter and radiation within it become more dilute. The total number of particles in a co-moving volume remains roughly constant, but as the volume expands, the energy density, the energy per unit volume, drops. For non-relativistic matter, this energy density decreases roughly as the inverse cube of the scale factor. For ultra-relativistic particles, the energy density declines even faster, roughly as the inverse fourth power of the scale factor. This is because the energy of fast-moving particles is dominated by their motion rather than their mass. So as the universe expands, each particle not only becomes more spread out but also loses energy as its momentum decays. Cosmologists often model the universe's contents as a perfect fluid with pressure related to energy density by a simple parameter called the equation of state. The energy density of such a fluid decreases as the scale factor grows according to the formula. Non-relativistic matter has, while radiation has, exotic components like dark energy can have negative, if the energy density remains constant over time, as is expected for a cosmological constant. If, representing the so-called phantom energy, the energy density actually grows as the universe expands. A particularly dramatic phase of the universe's history is inflation, a hypothesized period of extremely rapid expansion that occurred around 10 to the minus 32 seconds after the Big Bang. Inflation is thought to have been driven by a hypothetical field called the inflaton, which possessed a high-energy false vacuum state. This period of accelerated expansion was originally proposed to solve the puzzle of why certain exotic relics, like magnetic monopoles predicted by grand unified theories, are not observed. The rapid stretching of space would have diluted them to unobservably low densities. Inflation also naturally resolves the horizon problem, why the universe looks uniform across vast distances, and the flatness problem, why the universe appears geometrically flat. During inflation, tiny quantum fluctuations were stretched to cosmic scales, providing the seeds of the density variations that gravity later amplified into the galaxies, clusters, and voids we observe today. During this extraordinary expansion, the cosmic scale factor increased exponentially with time. For inflation to successfully solve the horizon and flatness problems, it needed to last long enough that the scale factor grew by at least a factor of e to the power of 60, which is roughly a factor of 1 followed by 26 zeros. This colossal stretching set the stage for the universe as we know it. The story of the universe in the moments immediately after cosmic inflation, but before roughly 1 second had passed, remains largely a mystery. Scientists have very few concrete details about this earliest phase, though they do know that by the time the universe was about 1 second old, it was filled with extremely energetic particles described by the standard model of particle physics. These particles move so fast that they are called ultra-relativistic, and collectively they are referred to as radiation. During this period dominated by radiation, the universe was expanding, but the expansion was slowing down gradually. Mathematically, the scale factor, which describes how distances in the universe grow over time, increased proportionally to the square root of the elapsed time. As the universe continued to grow, radiation gradually lost energy because its wavelength stretched along with the expansion. Eventually, the energy density of non-relativistic matter, particles that move much more slowly than light, overtook that of radiation. According to the standard cosmological model, this transition from radiation domination to matter domination happened roughly 50,000 years after the Big Bang. Once matter took over, the expansion of the universe still slowed down, but the scale factor now grew as the two-thirds power of time. This era, dominated by non-relativistic matter, was crucial for the formation of the cosmic structures we see today. Gravity could now effectively pull matter together, leading to the birth of galaxies, clusters of galaxies, and the vast cosmic web that structures the universe on its largest scales. Much later, approximately 3 billion years ago, when the universe had aged to around 11 billion years, a new actor took control: dark energy. Unlike matter or radiation, dark energy does not thin out as the universe expands. Its energy density remains roughly constant, and it gradually became the dominant component of the cosmos. When dark energy took over, it caused the expansion of the universe to accelerate. Similar to the rapid expansion that occurred during inflation, dark energy drives an exponential growth of the scale factor, meaning distances between faraway galaxies increase ever faster over time. To measure how quickly the universe is expanding, astronomers look at both the speeds at which galaxies are moving away and their distances. The ratio of speed to distance gives the so-called Hubble rate, in line with Hubble's law. Distances are often determined using standard candles, objects whose true brightness is well known. By comparing how bright they appear from Earth to how bright they actually are, scientists can calculate their distance. Meanwhile, the speed at which a galaxy recedes is measured through the redshift of its light, the stretching of light waves due to cosmic expansion. Edwin Hubble himself applied this method by observing Cepheid variable stars in nearby galaxies, using their brightness and redshifts to estimate the universe's expansion. More recent measurements use type Ia supernovae, exploding stars of a very specific type, to measure the Hubble rate with even greater precision. According to these observations, the Hubble constant is approximately 73.24 km per second per megaparsec, with a margin of error of plus or minus 1.74. In simpler terms, for every million parsecs of distance from Earth, a galaxy's recession speed increases by roughly 73 km per second, or about 160,000 miles per hour. Supernovae are so bright that they can be observed at enormous distances, sometimes so far that their light has been travelling almost as long as the universe has existed. This allows astronomers not only to measure the current expansion rate, but also to trace how the expansion has changed over cosmic history. Observations of these distant explosions led to the discovery, recognized by the Nobel Prize in Physics in 2011, that the universe's expansion is accelerating today. Another way to estimate the expansion rate relies on studying the cosmic microwave background, CMB, the faint afterglow of the Big Bang. In particular, the size of the largest fluctuations in the CMB depends on the expansion rate. A faster expanding universe results in smaller observed fluctuations, while a slower one results in larger fluctuations. Using this method, the Planck satellite mission calculated the Hubble constant to be roughly 67.4 km per second per megaparsec, with a very small uncertainty of plus or minus 0.5. The difference between this value and the one obtained from supernova observations is known as the Hubble tension, a puzzle that remains unresolved. A more recent approach is to use gravitational waves, ripples in spacetime produced by events like the merger of neutron stars. For instance, the event G-Besonsford 8.7 allowed scientists to attempt an independent measurement of the universe's expansion. While promising, these measurements are not yet precise enough to resolve the Hubble tension. In principle, the expansion history of the universe could also be measured by observing tiny changes in the redshifts, distances, brightness, or apparent sizes of astronomical objects over long periods, a method called redshift drift. Current technology is not sensitive enough to detect these subtle effects, but future instruments like the Square Kilometre Array and the Extremely Large Telescope, expected in the mid-2030s, could make such measurements possible. Communicating the nature of cosmic expansion is surprisingly tricky, and some of the language used in textbooks and popular science has led to misunderstandings. One common misconception is that the expansion of the universe means that space itself stretches while galaxies remain stationary. This is misleading because it implies a special reference frame, which violates Einstein's principle of relativity. The more accurate way to picture it is that galaxies are moving away from each other through space. Hubble's law also implies that galaxies beyond a certain distance, known as the Hubble horizon, recede faster than the speed of light. This is not a violation of special relativity, which applies to small, flat regions of spacetime, whereas the universe on large scales is curved. Close galaxies move relative to each other at speeds well below light speed. Only when considering the universe as a whole do these apparent superluminal velocities appear. It is also important to note that the relative velocity between very distant objects is not a simple concept. In the curved spacetime of the universe, there is no unique way to define the angle between 2 points separated by vast distances, so velocity on cosmic scales must be carefully interpreted. Another common mistake is to think of cosmic expansion as a force that pushes galaxies apart. In reality, expansion does not act like a repulsive force. It is simply a description of how galaxies are moving apart due to their initial motions. Dark energy, or the cosmological constant on the other hand, does produce an effect similar to a repulsive force that accelerates expansion. But this is a separate phenomenon. Interestingly, while the expansion of the universe is often framed as a prediction of Einstein's general relativity, it can also be derived using Newtonian gravity, provided it's expressed in a more sophisticated geometrical form developed by Élie Cartan. This approach avoids the conceptual problems Newtonian gravity encounters in an infinite universe. Other methods model the universe as a finite number of particles rather than a continuous fluid, but all these approaches converge to the same basic picture of an expanding cosmos. If a star or an entire galaxy is moving toward us, its light waves get squeezed and the light shifts a little toward the blue side of the spectrum. We call this blue shift. If the star or galaxy is moving away, the light waves stretch out instead, shifting toward the red side. That is what scientists call the red shift. In the years of the 1910s and 1920s, astronomers began using this smart trick to measure the movements of stars and galaxies. Among them was a man who would forever change how we see the universe, Edwin Hubble. His discoveries were truly amazing. When Hubble looked at distant galaxies, he found that most of them were not sitting quietly in space. Instead, they were speeding away from us. Even more surprising, the farther away a galaxy was, the faster it was moving. Some were moving at hundreds of kilometers per second, while others were rushing away at thousands. Every new observation confirmed the pattern. The farther, the faster. This could only mean one thing. Space itself was stretching, and galaxies were just carried along with it. It was one of the greatest discoveries in the history of science. It told us that the universe had a beginning, that everything we see today was once packed much closer together. It even set the stage for what would later be called the Big Bang Theory. But not every galaxy is moving away. One in particular stood out, a massive spiral-shaped neighbour that we know as the Andromeda Galaxy. In the year 1912, an American astronomer named Vesto Melvin Slipher pointed his telescope toward Andromeda and studied its light. At that time, the idea of redshift and blueshift in galaxies was still very new. What Slipher found shocked everyone. Andromeda's light was not redshifted, like almost every other galaxy. It was blueshifted. That meant it was not moving away from us. It was heading straight toward us. Back then, astronomers could only say that Andromeda was moving toward us. They did not have the tools to see the full picture. But fast forward 100 years, and the story becomes clearer. Today we have powerful space telescopes, giant supercomputers, and networks of radio dishes spread across the Earth. Astronomers combine data from NASA's Hubble Space Telescope, the Very Precise Gaia mission, and the Very Long Baseline Array of radio antennas. By carefully tracking Andromeda's motion over many years, they made a full three-dimensional map of its path. The result was clear. Andromeda is not just drifting nearby, nor will it pass by us safely. It is on a direct collision course with our own Milky Way galaxy, and we are moving toward it too. Right now, Andromeda is rushing toward us at about 110 kilometers per second. That equals more than 400,000 kilometers every single hour. But the Milky Way is not standing still either. Our whole galaxy, including the motion of our local group of galaxies, is moving toward Andromeda at nearly 300 kilometers per second. Added together, that means the gap between us is closing at an astonishing speed of about 500 kilometers per second. Yet space is unbelievably huge. Andromeda is roughly 2.5 million light-years away. That distance equals about 24 quintillion kilometers, a number so unimaginably large it almost loses meaning. So even though the two galaxies are rushing toward each other at incredible speeds, the meeting will not happen tomorrow, nor next year, nor even in the next million years. The actual collision will take place in about 4 to 5 billion years. Now, it might be tempting to imagine this galactic meeting as a fiery crash, stars smashing into stars, chaos, destruction, and explosions everywhere. But that is not how it will happen. Galaxies, despite their bright look, are mostly empty space. The stars inside them are extremely far apart from each other. Here in our part of the Milky Way, the average distance between two stars is about 4 to 5 light-years. That equals nearly 40 trillion kilometers. Even in the densest areas, stars are usually separated by at least a full light-year. To imagine it, if one star were the size of a ping-pong ball, the nearest star would be several hundred kilometers away. This means that when the Milky Way and Andromeda finally collide, most stars will just move past one another, untouched, like ships gliding silently at night. Still, it will not be completely calm. In the crowded center areas, some stars might actually collide. Others, especially those at the outer edges, could be thrown completely out of their galaxies, sent into the dark space between galaxies. But the real fireworks will not come from stars hitting each other. They will come from gravity. This invisible force will stretch, twist, and reshape both galaxies. Long, thin tails of stars will be pulled out like streamers. Spiral arms will be torn apart. The dense centers will be pulled closer and closer until the two galaxies finally join into one enormous, messy system. The full joining will not happen instantly. The first pass will be fast and close, starting the chaos. But the full merger, the slow gravitational dance, will take about 1 to 2 billion years to finish. It will not be a violent crash. It will be more like a long, graceful cosmic dance. And when the dance is over, something new will be born. The Milky Way and Andromeda will merge into a single giant round galaxy. Astronomers have even given it a name, Milkomeda. It will not have the elegant spiral arms we see today. Instead, it will become rounder, puffier, and brighter. A glowing ball of stars, gas, and dust. Our Sun, if it still exists, will likely end up in a new orbit, very different from the one it has today. It may drift farther from the center, following a more irregular path through this reshaped galaxy. Yet this story of Andromeda and the Milky Way is not the end. It is only one part of the much bigger journey our galaxy is taking. Together with Andromeda and hundreds of other nearby galaxies, we're all being pulled towards something even bigger and stranger. To understand where we are really going, we must zoom out far beyond the solar system, past the Milky Way itself, and even beyond our local group of galaxies. For galaxies are not scattered at random. They gather in clusters, pulled together by gravity flowing across space like water moving downhill. Our Milky Way is not alone in space. It belongs to a family of galaxies known as the Local Group. This group contains roughly 80 galaxies, both big and small, spread out across a space about 10 million light-years wide. Within this family, the two giants stand out, our own Milky Way and the huge Andromeda galaxy. Each of these big galaxies is surrounded by smaller companions called satellite galaxies that orbit them like moons around a planet. For the Milky Way, these include the large and small Magellanic Clouds. For Andromeda, tiny galaxies like Messier 32 and Messier 110 spin around it like loyal followers. But the Local Group is just one small neighborhood in the much larger cosmic city. Step one level higher and you reach galaxy clusters. These are huge gatherings of galaxies, where several galaxy groups are held together by gravity. Our Local Group is a small part of the Virgo cluster, a vast collection of more than 1,000 galaxies. The Virgo cluster is about 65 million light-years away, and its gravity pulls on us constantly. We are not floating aimlessly near it. The entire Local Group, including the Milky Way, is moving toward the Virgo cluster's center at a breathtaking speed of roughly 600 kilometers per second. Yet even clusters are not the largest structure in space. Clusters themselves can gather into even bigger formations called superclusters, the largest formations in the observable universe. These cosmic giants can stretch across hundreds of millions of light-years and hold tens of thousands of galaxies. Our home supercluster is named Laniakea, a Hawaiian word meaning immense heaven. The name fits well, for Laniakea is truly huge, spanning more than 500 million light-years and holding nearly 100,000 galaxies. Within it lie well-known clusters such as Virgo, Hydra Centaurus, Pavo Indus, and the Southern Supercluster, all connected by a delicate cosmic web of galaxy flows. How then do scientists know all this? How can they tell where galaxies are, how fast they move, and which way they are heading? The answer lies in studying motion. Over the past decades, astronomers have not only mapped where galaxies sit in the sky, but also followed their movements. To do this, they needed more than the familiar redshifts and blue shifts that show galaxies moving away or toward us. They had to measure something trickier, peculiar velocity, which is the motion of galaxies compared to the general expansion of the universe itself. Measuring this sideways drift through space is not easy. You cannot just take a picture and know. Astronomers rely on smart tools, one of the most important being the Tully-Fisher relation. This method connects the brightness of a spiral galaxy with how fast it spins. By comparing how bright a galaxy should be to how bright it actually looks from Earth, astronomers can guess its distance. And if they know both the distance and the redshift, they can tell whether the galaxy is moving faster or slower than the universe's general expansion. That difference shows its peculiar speed, movement caused by nearby gravitational pulls rather than the universe spreading out alone. These measurements became the base for the cosmic flows surveys, Cosmic Flows 2, and later the even more detailed Cosmic Flows 3 collected huge amounts of data mapping the movements and distances of thousands of galaxies. They used methods such as the Tully-Fisher relation, surface brightness changes, and even Type Ia supernovae as cosmic measuring sticks. With this information, scientists built a three-dimensional map of speeds in our cosmic neighborhood, showing not just where galaxies are, but how they are moving through space, and the results were amazing. The galaxies were not just scattering outward like dots on a blowing-up balloon. Instead, they were moving together in one direction, flowing toward a mysterious region hidden behind the thick dust of our Milky Way, somewhere beyond the constellation Centaurus and Norma. This hidden source of gravity became known as the Great Attractor. The Great Attractor was first guessed in the 1970s, when astronomers saw that galaxies, including our own, were sliding sideways through space at hundreds of kilometers per second, as if pulled by something huge. Yet when telescopes looked in that direction, they hit the so-called zone of avoidance, a crowded stretch of sky blocked by the Milky Way's own stars, dust and gas. Still, the movement could not be ignored. The gravitational pull was real, even if the object itself could not be seen directly. Over time, with the help of X-ray telescopes and infrared surveys that could look through the dust, astronomers put the pieces together. They found huge masses of galaxies grouped in that hidden region. One of the biggest was the Norma cluster, lying about 220 million light-years away. But Norma was not alone. It was part of something far bigger, the Shapley supercluster, one of the largest known groups of clusters in our local universe. The strong gravity of the Shapley supercluster bends the paths of galaxies across huge areas of space, and it is this massive structure that is pulling our local group, our Virgo cluster, and even the whole Laniakea supercluster in its direction. Yet our journey is not a straight fall into this cosmic giant. Space is not a simple playground, and gravity does not act like a rope pulling in one direction. Instead, we are caught in a cosmic tug-of-war. While the Great Attractor and Shapley supercluster pull us one way, another force shapes our path in a very different way, the mysterious dipole repeller. The dipole repeller is not an object. It is not a cluster or even a galaxy. It is a cosmic empty space, a huge, nearly matter-free region of space, and emptiness, strangely enough, has power. While massive objects pull galaxies toward them, huge empty spaces act like open gates, letting galaxies drift away more easily. Imagine floating in a river. On one side, a roaring waterfall pulls you forward. That is the Great Attractor. On the other side, the water is calm and flat. That is the dipole repeller. You're not being pushed by it, but you're not held back either. Naturally, the waterfall wins, and you drift toward it. In the year 2017, Using data from Cosmic Flows 3 that map the motions of over 18,000 galaxies, astronomers finally confirmed this picture. They saw not only a pull toward the Great Attractor, but also a flow away from the dipole repeller, a two-way pattern shaping the movement of galaxies across the nearby universe. And when you zoom out even farther, beyond galaxies, clusters, superclusters, beyond the threads and empty spaces, an even bigger movement becomes clear. The large threads of the cosmic web themselves are not fixed. They too are drifting, sliding and flowing across the huge stretches of the observable universe, all moving towards some bigger, still hidden destination. As the universe keeps stretching and growing, something truly breathtaking is happening. The galaxies that are far from us are drifting even farther, and they are moving faster and faster. It is not because they are racing through space like rockets. The truth is even more amazing. The very fabric of space itself is stretching, and as it stretches, it carries those galaxies along, as if they are passengers on an invisible current. This great stretching of space is not slowing down. Quite the opposite, it is speeding up. Scientists call this the accelerating expansion of the universe. This means that with every passing moment, galaxies are moving away from us faster and faster. The farther a galaxy is from us, the faster it seems to move away. And one day, some galaxies will be moving away so fast that, from our view, they will seem to go faster than the speed of light. At first, this sounds like it breaks the rules of nature because we often hear that nothing can move faster than light. But here is the twist. Those galaxies are not actually breaking any cosmic speed limits. They are not moving through space that fast. Instead, it is the space between us and them that is growing. This stretching of space is allowed by the laws of physics. You can think of it like raisins in bread dough. The raisins are not rushing around inside the dough, but as the dough rises and grows, the raisins are pushed farther and farther apart. This is very important, because it tells us something amazing about the future of the universe. A future that is both fascinating and a little lonely. As space keeps expanding, the most distant galaxies will drift so far away that even their light will never reach Earth again. They will vanish from our sight, not because they are gone, but because their light can no longer keep up with the swelling space. At that point, they will cross what scientists call the cosmic horizon, the ultimate limit of what we can ever hope to see. This is not some distant dream. It is already happening. Right now, there are galaxies so unimaginably far away that the light we see from them today began its journey billions of years ago. And as the years pass, that light will be stretched more and more by the expanding space. This stretching of light is called redshift, because it pushes the light toward the red end of the color spectrum. The faster a galaxy moves away, the more stretched and redshifted its light becomes. Eventually, the light from these galaxies will be stretched so much that it will go beyond what our eyes and even the most powerful telescopes can see. First, it will slide into the range of microwaves, then into radio waves, and finally it will disappear completely into the darkness. If we jump forward billions of years into the future, most of the galaxies in the universe will have already disappeared beyond our cosmic horizon. The only ones that will still be visible to us will be those that are held together by gravity, our small cosmic family. These galaxies make up what astronomers call the local group, which includes our Milky Way, the mighty Andromeda galaxy, and a few smaller galaxies nearby. Because gravity holds them together, these galaxies will not drift apart. Instead, over time, they will slowly move closer and eventually merge into one huge galaxy. Beyond this small family, however, the rest of the universe, with all its galaxies, stars and wonders, will quietly slip out of view, one by one, into the endless dark. This shows a universe that becomes lonelier as time goes on. Each distant galaxy that disappears takes with it its light, its history, and its part in the big cosmic story. Future astronomers, living trillions of years from now, may look at the night sky and see only one massive galaxy, the final union of the Milky Way and its neighbours. They might never know that once there was a huge universe full of countless galaxies beyond their view. In the early days of the universe, galaxies often collided and merged, causing bursts of starbirth and big changes. But as centuries and millennia stretch into billions of years, and galaxies drift farther apart, such fiery encounters will become rare. The universe will grow quieter, calmer, and much more alone. And in the far, far future, long after the last galaxy has gone beyond our sight, the universe will change even more. The stars in our galaxy will keep shining for billions of years, but eventually even they will run out of fuel. No new stars will be born. One by one, the stars will fade, and the universe will grow colder and darker. This final chapter is called the heat death of the universe, a time when all energy is used up, when stars and galaxies no longer burn, and when the cosmos itself falls into deep stillness. So far, the expansion of the universe has not changed the rules of physics, but it has stretched the way those rules play out on the larger scales. The basic rules, gravity, heat and energy, quantum behavior, still hold firm. Yet the conditions under which they act are changing, shaping the future of everything we see. Still, some scientists wonder, could this endless stretching of space eventually change the very rules of nature themselves? It is a bold and thought-provoking question, one that challenges the old belief that the constants of physics, like the speed of light, the strength of gravity, or the tiny forces that shape how light interacts with matter, are fixed and eternal. What if they are not? These constants are like the very building blocks of reality, the invisible scaffolding on which the universe stands. Take the speed of light, for instance. It is not just about how fast light travels, it is the ultimate speed limit for everything, for all information and matter in the cosmos. Nothing can surpass it. Then there is the gravitational constant, which sets the strength of gravity. It is what keeps the moon tethered to the Earth, the planets bound to the sun, and even entire galaxies held together. Without this invisible force, stars would never shine, planets would not form, and galaxies would drift apart into empty darkness. In short, without these constants, the universe as we know it would not exist at all. So far, every experiment and observation tells us that these constants remain steady. Even as the universe stretches and grows ever larger, the rules seem to hold firm. Yet, when we gaze far into the distant future, we cannot help but wonder, is this foundation truly unchanging? Or might there be a hidden twist in the story of reality waiting to appear? Another crucial player in the cosmic tale is something called the fine structure constant. This is a special number that governs how light and tiny charged particles, like electrons and protons, interact. It is central to chemistry, determining how atoms cling together and how matter behaves. Even the slightest shift in this number could transform the universe entirely. Imagine a world where atoms could not exist, where stars never ignite, and life as we know it could never appear. This one small number carries the power to shape everything, and then the story grows even more astonishing. The universe is not static, it is expanding, driven by the mysterious force we call dark energy. Space itself stretches, almost like a balloon that keeps inflating. This stretching pushes galaxies apart and sculpts the cosmos on an immense and awe-inspiring scale. But could this cosmic stretching also affect the very rules that govern everything within space? Some scientists think this might be possible. They suggest that the constants we measure today, such as gravity or the strength of electromagnetic forces, may not have been exactly the same in the past. Perhaps billions of years ago the universe played by slightly different rules. If so, the early universe might have looked very different, shaping how the first stars, galaxies and clusters were born. Among these constants, the fine structure constant has drawn particular attention. Some studies hint that this number might have been just a tiny bit different billions of years ago. This idea remains controversial and far from proven, but if it were true, it could mean that the universe's expansion, or other unknown cosmic forces, can slowly nudge the laws of physics themselves. Then there is dark energy, a force that continues to baffle scientists. We do not yet fully understand what it is or how it acts. Some theories suggest that dark energy may be tied to the universe's evolving nature, perhaps even subtly influencing the fundamental constants of physics over unimaginable spans of time. The mysteries grow even stranger. Some researchers have speculated that the stretching of space might influence time itself. As distances between galaxies grow and light waves lengthen, could time also be stretching along with space? Could the very rhythm of the cosmos, the passage of seconds, minutes and eons, be subtly shifting as the universe expands? Even more extraordinary ideas have been imagined. Over incredibly long periods, as the universe expands and cools, it might eventually undergo massive transformations, known as phase transitions. These are similar to how water turns to ice when it gets cold enough, but on a cosmic scale. In such a transformation, the universe could enter an entirely new state, where the laws of physics themselves might rearrange, old rules vanish and new ones take their place. This could happen trillions upon trillions of years from now, leaving a cosmos utterly unrecognizable, a reality beyond the limits of our imagination today. In every moment, as we explore the universe and peer deeper into its past and future, we see that these constants, these invisible laws, are both steadfast and mysterious. They shape everything, yet perhaps in ways we do not yet fully understand, they might not be eternal. The universe is not just vast, it is alive with questions, with possibilities, and with wonders that stretch far beyond the reaches of our minds. In the field of physical cosmology, there is a fascinating idea known as cosmic inflation, sometimes called cosmological inflation, or simply inflation. This theory suggests that in the very first moments after the universe began, space itself expanded at an incredible, almost unimaginable speed, growing exponentially in a tiny fraction of a second. After this extraordinary burst of expansion, the universe kept stretching outward, but more slowly, as the vast cosmic canvas continued to unfurl. Much later, when the universe had already reached an age of over 7,700,000,000 years, it began to accelerate again, driven by the mysterious force known as dark energy. This reacceleration started about 5,400,000,000 years ago. The theory of inflation first took shape in the late 1970s and early 1980s, thanks to the groundbreaking work of several brilliant theoretical physicists. Among them were Alexei Starobinsky, working at the Landau Institute for Theoretical Physics, Alan Guth from Cornell University, and Andrei Linde of the Lebedev Physical Institute. Their collective contributions were so important that, in the year 2014, they were awarded the prestigious Kavli Prize for pioneering the theory of cosmic inflation. Throughout the early 1980s, their work was further developed and refined, helping to explain some of the most puzzling features of the universe. One of the most remarkable insights of inflation is how it seeded the large-scale structure of the cosmos. In the earliest tiny patch of space that experienced inflation, quantum fluctuations, tiny, random variations at the smallest scales imaginable, were stretched enormously, eventually growing into the vast structures we see today, including galaxies, clusters of galaxies, and the cosmic web itself. This process helps explain why the universe appears largely uniform in all directions, why the cosmic microwave background radiation, the faint afterglow of the Big Bang, is so evenly spread, why the overall geometry of the universe seems flat, and why certain hypothetical objects such as magnetic monopoles have never been observed. Despite its successes, scientists still do not know the exact particle physics mechanism behind inflation. Nevertheless, many predictions of the theory have been confirmed by observations. For instance, in 1992, the COBE satellite detected tiny variations in temperature across the cosmic microwave background that matched the nearly scale-invariant patterns predicted by inflation. Later, the WMAP mission provided even stronger evidence supporting inflation. Some researchers, however, remain skeptical and continue to debate aspects of the theory. The mysterious field believed to drive inflation is called the inflaton, though its nature remains hypothetical. In recognition of the immense impact of this theory, several of its key developers received additional honours. In 2002, Alan Guth, Andrei Linde, and Paul Steinhardt shared the Dirac Prize for their development of inflationary ideas. A decade later, in 2012, Guth and Linde received the Breakthrough Prize in Fundamental Physics for their revolutionary work on inflationary cosmology. To understand the scale of cosmic inflation, consider this. During the brief inflationary period, which lasted at least 10 to the power of minus 35 seconds, distances between points in space doubled every 10 to the power of minus 37 seconds. In other words, space expanded at an almost inconceivable rate. Everything that now makes up all the visible galaxies, stars, planets, gas and dust, was once contained within a sphere with a radius of roughly 4 times 10 to the power of minus 29 meters. By the end of inflation, this tiny sphere had grown to a radius of nearly 1 meter. Once inflation ended, the energy driving this rapid expansion transformed into particles, creating a hot, dense soup of quarks and other fundamental particles, while leaving behind subtle density variations from the original quantum fluctuations. These tiny variations later acted as the seeds for the formation of stars and galaxies. Inflation also helped solve several long-standing problems in the traditional Big Bang model. While the Big Bang theory successfully explained the cosmic microwave background and the formation of the first elements, it relied on assumptions about the initial conditions of the universe that were difficult to justify. For example, the Big Bang on its own could not naturally create the density fluctuations necessary for galaxies to form, because a perfectly uniform early universe would not have had the gravitational clumps needed for matter to come together. Inflation provided a mechanism for generating these variations. Another major challenge involved magnetic monopoles, hypothetical particles predicted by certain grand unified theories, which suggest that at extremely high temperatures in the early universe, the electromagnetic strong and weak nuclear forces were unified. These theories implied the creation of heavy, stable monopoles that should still exist today in large numbers. Yet, despite extensive searches, no magnetic monopoles have ever been detected. Inflation offers a solution. If the universe expanded rapidly below the temperature at which monopoles could form, it would stretch the space between them so greatly that their density became vanishingly small, explaining why we do not see them. While the initial motivation for inflation arose from problems like monopoles, it also elegantly addressed other mysteries. It explains why the universe appears so flat, a puzzle known as the flatness problem, and why regions of the universe that should never have been in contact still share the same temperature, known as the horizon problem. Although some scientists remain cautious, noting that the solution might seem like preventive medicine against a disease that does not exist, inflation remains one of the most powerful and widely studied ideas in cosmology, helping to illuminate the extraordinary story of how the universe came to be structured as we see it today. The flatness problem, sometimes also called the oldness problem, is one of the puzzles about the early universe in the Big Bang model. Observations of the cosmic microwave background, the faint glow left over from the early universe, show that the universe is remarkably flat, at least within a few percent. In cosmology, flat means that space is not curved like a sphere or saddle, but more like a smooth, infinite plane. Interestingly, the expansion of the universe actually pushes it closer to being flat over time. This means that if the universe is as flat as we see it today, it must have been incredibly close to perfectly flat in its earliest moments. In the standard cosmological picture, based on the equations developed by Alexander Friedmann, the curvature of space-time depends on the total density of matter and energy in the universe. There is a very precise critical density that corresponds to a perfectly flat universe. Observations show that today, the density of the universe is extremely close to this critical value. But here's the catch. If the density had been even slightly different in the early universe, this difference would have grown enormously over time. To match what we see today, the early universe must have had a density fine-tuned to this critical value to an astonishing degree, differing by no more than 1 part in 10 to the power of 62. This extreme fine-tuning naturally makes scientists wonder, how did the universe start out with such a special density? The horizon problem is another puzzle about the early universe. It asks why the universe looks so uniform, why it appears roughly the same in all directions and at all locations, a property called homogeneity and isotropy. To understand the problem, imagine a canister of gas. The molecules inside eventually spread out evenly and reach the same temperature because they have time to interact and reach equilibrium. In the standard Big Bang model without inflation, parts of the universe move apart so quickly that widely separated regions do not have time to communicate or share information. They cannot come into thermal equilibrium because they are receding from each other faster than the speed of light. Essentially, regions too far apart could never have exchanged signals, so why do they appear so similar? Inflation theory provides a solution to both the flatness and horizon problems. According to this theory, the universe began as a tiny, hot and uniform patch in thermal equilibrium. Then, almost unimaginably quickly, it expanded exponentially, faster than the speed of light, for a tiny fraction of a second. This rapid expansion stretched the equilibrated regions so far apart that, by the time normal gravitational expansion took over, the universe appeared smooth, uniform and isotropic on large scales. In this way, inflation sets up the ideal initial conditions for the universe's expansion, as described by general relativity. As the universe expands, it also develops a cosmological horizon. This horizon is similar to the horizon you see when looking across the Earth. It marks the farthest distance from which light or any signal can reach an observer. Anything beyond this horizon cannot be seen or influenced because space between the observer and the object is expanding too quickly. The observable universe, the portion we can see, is just one patch of a much larger universe. Many other regions lie beyond our cosmological horizon and have not yet been able to communicate with us. Current estimates suggest that this horizon extends about 46 billion light-years in every direction from Earth. In the standard hot Big Bang model without inflation, the horizon gradually moves outward, bringing new regions into view. Yet, when we observe these new regions, they look remarkably similar to the regions we already know. Their background radiation has nearly the same temperature, and the curvature of space-time evolves in step with the rest of the universe. This presents a deep mystery. How did these regions know what temperature and curvature they were supposed to have if they were never in contact with one another? Inflation theory elegantly explains this. By stretching a tiny uniform region to enormous scales, it ensures that all widely separated parts of the observable universe share the same initial conditions. Inflation predicts that the total curvature of a slice of space at a constant cosmic time is essentially zero. This means that the sum of all ordinary matter, dark matter, and vacuum energy in the universe must equal the critical density, and observations strongly support this prediction. More impressively, inflation also explains tiny differences in temperature across the sky. These minute variations come from quantum fluctuations during the inflationary era, and many of the predictions based on these fluctuations have been confirmed by observation. If we try to look back in time at the universe when it was smaller, denser, and filled with unimaginable energy, we eventually reach a point where our current understanding of physics may no longer apply. At these extreme conditions, the usual rules of nature, the ones that govern atoms, light, and gravity today, might not hold at all. It is here that the idea of cosmic inflation comes into play. The inflation hypothesis proposes that, in this very early epoch, space itself expanded at an astonishing, almost unbelievable pace, growing exponentially by enormous amounts in a tiny fraction of a second. In a universe undergoing such rapid expansion, any two objects that are initially just floating freely in space will start moving apart from each other faster and faster, as long as nothing is holding them together. From the viewpoint of one of these objects, the universe behaves in a strange way. It is as if the object is at the center of an inside-out black hole. Surrounding it is a spherical boundary, called an event horizon, beyond which anything that passes can never return. Light or signal sent by the distant object can never reach the first one, as long as this explosive expansion continues. If the expansion were perfectly exponential, this horizon would remain fixed at a certain physical distance. However, in reality, inflation is not perfectly exponential, but almost so. Because of this, the horizon slowly moves outward as the energy driving inflation, the vacuum energy, gradually decreases. One of the most remarkable consequences of inflation is how it smooths the universe. Any small wrinkles in the density or temperature of the early universe get stretched out over enormous distances. This makes the universe extremely uniform and almost perfectly flat. During inflation, the universe becomes dominated by a mysterious field called the inflaton, and the only remaining tiny irregularities are quantum fluctuations, minuscule differences that eventually seed the formation of galaxies and stars. Inflation also has the effect of washing away exotic, heavy particles that some theories of particle physics predict, like magnetic monopoles. Even if such particles were created before inflation, the expansion would spread them so thinly across space that they would be practically undetectable in the observable universe. Together, these smoothing effects are sometimes referred to as the inflationary no-hair theorem, drawing an analogy with the black hole no-hair theorem, which suggests that black holes lose almost all distinguishing features except mass, charge, and spin. The reason this no-hair effect works is closely related to the concept of a horizon in cosmology. Just as a black hole has a horizon beyond which nothing can escape, during inflation the universe has a cosmological horizon. As the universe expands enormously, the energy in ordinary matter and radiation gets diluted. For example, the energy density of regular cold matter, imagine dust scattered across space, decreases as the universe grows. If the universe doubles in size in every direction, the energy density of this matter falls by a factor of 8. Radiation, such as light, thins out even faster. Not only does the expansion spread photons apart, but their wavelengths stretch, a process called redshift. If the universe doubles in size, the energy density of radiation falls by a factor of 16. Meanwhile, the energy stored in the inflaton field remains nearly constant, dominating everything else. With enough inflation, the energy from curvature, irregularities, anisotropies, and exotic particles all become negligible. By the time inflation ends, the universe is extraordinarily flat, uniform, and mostly empty, aside from the inflaton field itself. Inflation is also a time of supercooled expansion. The temperature of the universe drops dramatically during this phase, by a factor of roughly 100,000. In early models, this meant the temperature fell from around 10 to the 27th degrees Kelvin down to 10 to the 22nd degrees Kelvin. The universe remains at this low temperature throughout inflation. When inflation finally stops, the universe reheats. This process, known as reheating or thermalization, occurs as the immense potential energy of the inflaton field decays into particles, filling space with ordinary matter and radiation. This marks the start of the radiation-dominated phase of the universe. Exactly how this happens is still not completely understood, because the true nature of the inflaton field remains a mystery, but physicists believe it involves a process called parametric resonance, where the energy of the field transfers efficiently into particles. In the very early days of Albert Einstein's theory of general relativity, he introduced what he called the cosmological constant. He did this because he wanted the equations of the universe to allow a static universe, one that neither expanded nor contracted. This theoretical universe was imagined as a three-dimensional sphere, perfectly uniform in its density of matter. However, not long after, the Dutch astronomer Willem de Sitter discovered a very different kind of universe, one that expanded rapidly and was highly symmetrical, containing a cosmological constant but otherwise empty of matter. Over time, scientists realized that Einstein's static universe was inherently unstable. Tiny disturbances, even the smallest fluctuations, would eventually cause it either to collapse under its own gravity or to transform into a universe more like de Sitter's, expanding endlessly. Over the years, many scientists proposed alternative ideas to understand how the universe could evolve. Georges Lemaitre suggested the Phoenix universe, a universe that continually rose from its own ashes through cycles of contraction and expansion. Richard Chase Tolman proposed a related idea called the oscillatory universe, which similarly envisioned a universe endlessly contracting and bouncing back in a new expansion. Both Lemaitre and Tolman imagined that through these repeated cycles, the universe might reach a kind of thermal equilibrium, where energy is evenly spread out. Unfortunately, their models failed because with each cycle, entropy, a measure of disorder, built up, preventing the universe from returning to a balanced state. Around the same time, Charles Misner proposed the Mixmaster universe, which introduced chaos into the early universe. He hoped that this chaotic behavior could somehow make the universe statistically uniform and smooth. In the end, this idea also did not fully succeed. In 1965, the physicist Horace Gleiner proposed a new and unique idea about the early universe. He suggested that the pressure in the universe was negatively related to the energy density, meaning that the more energy there was, the stronger the negative pressure. This simple relationship was revolutionary because it became the first theoretical hint at what we now call dark energy, the mysterious force driving the universe's accelerated expansion. By the early 1970s, cosmologist Yakov Zeldovich noticed some deep problems with the Big Bang model, including the flatness problem, why the universe appears so geometrically flat, and the horizon problem, why distant parts of the universe look so similar despite never having been in contact. Before this, cosmologists often assumed symmetry in the universe for philosophical reasons rather than physical evidence. In the Soviet Union, these ideas inspired Vladimir Belinsky and Isaac Kalatnikov to analyze chaotic behaviors in the universe's earliest moments, known as BKL singularities. Misner's Mixmaster universe was another attempt to use this chaos to explain cosmic uniformity, though it had limited success. Later, in the late 1970s, Sidney Coleman applied advanced quantum techniques developed by Alexander Polyakov and his colleagues to study how a false vacuum could decay. A false vacuum is like a supercooled liquid or superheated water. It is temporarily stable but can spontaneously shift to a more stable state. Coleman showed that for a universe trapped in a false vacuum, a large enough bubble of true vacuum could suddenly form and expand, potentially transforming the universe. He calculated how likely this decay was and how quickly it might happen per unit of space. Although he realized gravity would play an important role, he did not include gravitational effects in his calculations nor connect his results directly to cosmology. This line of thinking suggested a mind-blowing possibility. The universe could have spontaneously appeared from nothing, no space, no time, no matter, triggered by quantum fluctuations in a false vacuum that led to an expanding bubble of true vacuum. Building on these ideas, in 1978 and 1979, Robert Brute, François Englert, and Edgard Günzig proposed that the universe could start as a tiny fluctuation in empty space, known as Minkowski space, which would then briefly behave like de Sitter space, expanding rapidly. This early phase would eventually evolve into the familiar expanding universe we see today. Their model was especially elegant because it avoided particle or event horizons, making the universe entirely causal. Everything could, in principle, influence everything else. Meanwhile, in the Soviet Union, Alexei Starobinsky explored how quantum effects might modify general relativity in the very early universe. He discovered that these effects could lead to curvature-squared corrections in Einstein's equations, a type of modified gravity. When these corrections are large, the solution naturally produces a phase that behaves like a cosmological constant, driving exponential expansion. This led Starobinsky to propose that the early universe underwent an inflationary de Sitter phase, which solved several major cosmological problems and provided precise predictions for small variations in the cosmic microwave background radiation. In the same period, Zeldovich identified another puzzle, the magnetic monopole problem, which was a precise particle physics version of the horizon problem. Solving it required new ideas about the early universe. In 1980, Alan Guth realized that if the universe experienced false vacuum decay, it would naturally solve the monopole problem. Guth proposed the concept of scalar field-driven inflation, which, like Starobinsky's model, predicted an initial de Sitter phase. Both models shared the same broad picture but differed in details of the mechanism. Guth officially proposed his inflation theory in January 1981 to explain why magnetic monopoles were absent. He was also the one who coined the term inflation. Around the same time, Starobinsky argued that quantum corrections could replace the universe's supposed initial singularity with a phase of exponential expansion. Earlier, in October 1980, Demosthenes Kazanas suggested that such rapid expansion could eliminate the particle horizon, possibly solving the horizon problem. Similarly, Katsuhiko Sato suggested that exponential expansion could remove domain walls, exotic relics from the early universe. In 1981, Einhorn and Sato published a model similar to Guth's, showing that it could resolve the puzzle of magnetic monopoles predicted by grand unified theories. They also found that while the model needed fine-tuning of the cosmological constant, it risked creating too much variation in density, producing an overly granular universe from bubble wall collisions. Guth proposed that in the early universe, as it cooled, it became trapped in a false vacuum with a very high energy density, similar in effect to a cosmological constant. The universe was supercooled, meaning it was in a metastable state, and could only escape through bubble nucleation, a process allowed by quantum tunneling. Tiny bubbles of true vacuum would spontaneously appear in the sea of false vacuum and expand almost at the speed of light. However, Guth noticed a problem. This model did not reheat the universe properly. Radiation, which we need for the hot Big Bang, could only be generated when bubbles collided. But if inflation lasted long enough to solve the problems of the universe's initial conditions, these bubble collisions became extremely rare, leaving the reheating incomplete. The problem known as the bubble collision problem was eventually solved by the Russian physicist Andrei Linde and, at the same time but independently, by the physicists Andreas Albrecht and Paul Steinhardt. They introduced a new model called new inflation, sometimes also called slow-roll inflation, while the earlier idea proposed by Alan Guth became known as old inflation. In this newer model, the universe did not expand by suddenly tunneling out of a false vacuum state, as in Guth's original idea. Instead, the process was more gradual. A mysterious energy field, called the scalar field, slowly rolled down a kind of energy hill. As long as the field moved very slowly compared to the rapid expansion of the universe, inflation, the explosive growth of space, continued. But once the hill became steeper and the field sped up, inflation came to an end, and the universe could begin reheating, filling space with particles and radiation. Over time, scientists realized that new inflation did not create a perfectly smooth, uniform universe. Tiny random variations, or quantum fluctuations, appeared naturally in the inflaton field, the field responsible for inflation. These minute ripples became the seeds from which all the galaxies, stars, and cosmic structures we see today eventually grew. The first detailed calculations of these fluctuations were carried out by Vyacheslav Mukhanov and G.V. Chibisov while studying a model similar to one developed by Alexei Starobinsky. Around the same time, at a workshop held in Cambridge, England, in March of 1982, 4 independent groups of physicists also worked out these fluctuations. The groups included Stephen Hawking, Alexei Starobinsky, Alan Guth with So-Young Pi, and James Bardeen, Paul Steinhardt, and Michael Turner. Each team, working separately, arrived at similar results, confirming the robustness of the idea that tiny quantum ripples during inflation could grow into the large-scale structure of the universe. As it became clear that the cosmic microwave background, or CMB, could serve as a key testing ground for theories of the early universe, scientists began considering ways to check alternative ideas against observation. One such alternative, developed around the same time as Guth's work, involved cosmological topological defects. This idea suggested that as the early universe cooled from its initial hot and dense state, it experienced a series of sudden changes called phase transitions, similar to how certain materials like liquid helium form vortices as they change states. These topological defects arose from the complex structure of the universe's vacuum states, known as the vacuum manifold, after a symmetry-breaking transition. A famous example of a predicted stable topological defect is the magnetic monopole, a theoretical particle proposed by grand unified theories of the early universe. Over the course of the 1980s and 1990s, physicists refined these ideas and made predictions that could be tested through precise measurements of the CMB. In the end, detailed observations, especially those from the Wilkinson Microwave Anisotropy Probe, provided strong support for cosmic inflation, although hybrid models that include both inflation and topological defects are still considered possible. The concept of inflation is not just a solution to technical problems, it also provides a natural explanation for why the universe appears the way it does. It underlies the cosmological principle, which states that, on large scales, the universe is both homogeneous, the same everywhere, and isotropic, the same in all directions. Inflation also explains why the universe appears flat, why it lacks abundant magnetic monopoles, and why the CMB has the particular patterns we observe. These predictions have been confirmed and refined by increasingly detailed observations, most notably those from the Planck spacecraft. Planck's measurements show that the universe is flat to within 0.1%, and that it is uniform to 1 part in 100,000. Inflation predicts that the cosmic structures we see today, galaxies, galaxy clusters, and vast filaments of matter, formed from tiny primordial fluctuations caused by quantum effects during the inflationary period. These fluctuations have a very specific mathematical structure called a nearly scale-invariant Gaussian random field, which is determined by just 2 key parameters, the amplitude of the fluctuations, which measures their overall strength, and the spectral index, which measures how their size changes slightly across different scales. The spectral index would be exactly 1 in a perfectly scale-invariant universe, called a de Sitter universe, but in reality it deviates slightly from this ideal. A third important parameter is the tensor-to-scalar ratio, which measures the relative strength of gravitational waves generated during inflation compared to the density fluctuations. The simplest inflation models, without artificial fine-tuning, predict a tensor-to-scalar ratio of around 0.1. Inflation also predicts that the fluctuations should all be in thermal equilibrium with each other, meaning the variations in density are all correlated in a specific way, known as adiabatic or isentropic perturbations. These predictions have been confirmed with astonishing precision by Planck, WMAP, and other CMB experiments, as well as by large-scale surveys of galaxies like the ongoing Sloan Digital Sky Survey. These observations show that the tiny irregularities of 1 part in 100,000 appear exactly as predicted. The spectral index called DER is measured to be approximately 0.968 plus or minus 0.006, fitting comfortably within the range 0.92 to 0.98 expected from simple inflation models. Meanwhile, the tensor-to-scalar ratio is found to be less than 0.11, consistent with theory and confirming inflation's predictions. Although numerous alternative inflation models have been proposed, most require more intricate adjustments of parameters than seem necessary. The power of inflation lies in its simplicity. With just two adjustable numbers, the amplitude of the fluctuations and the spectral index, it robustly predicts the initial conditions of the universe. This holds true across a wide range of possible particle physics mechanisms for inflation. Sometimes, anomalies appear that seem to contradict the simplest inflation models. For example, the first-year WMAP data hinted that the spectrum of fluctuations might curve slightly, rather than being nearly scale invariant, though later analyses, including the third-year WMAP data, showed that this was just a statistical fluke. Another puzzling observation, noted since the Cosmic Background Explorer satellite, is that the CMB's quadrupole moment is lower than expected, and that the lowest multipoles are oddly aligned with the plane of the solar system. Some scientists argue this may hint at new physics, quantum effects, or even biases in data interpretation, but the simplest explanation is that inflation remains fundamentally correct, with these effects representing subtle complexities rather than contradictions. Scientists have been working on a series of experiments to test the theory of cosmic inflation more precisely, using increasingly accurate measurements of the cosmic microwave background, or CMB, the faint glow left over from the Big Bang. One particularly promising target is the so-called B-mode pattern in the polarization of this background radiation. Detecting these B-modes could reveal the gravitational waves produced during inflation and might confirm whether the energy scale predicted by the simplest inflation models, between 10 to the 15th and 10 to the 16th giga-electron volts, is correct. In March of 2014, the BICEP2 team announced that they had detected B-mode polarization in the CMB, claiming it as strong evidence for inflation. They reported that the ratio of tensor to scalar perturbations, known as R, fell somewhere between 0.15 and 0.27, which suggested that inflation had indeed left a measurable imprint. However, by the 19th of June 2014, doubts began to emerge, reducing confidence in these results. Further assessments on the 19th of September 2014 and again on the 30th of January 2015 continued to lower this confidence. By 2018, a combination of additional data suggested with 95% confidence that R was 0.06 or lower, consistent with no detectable inflationary signal, yet still compatible with several inflation models. Other potential confirmations may come from observations by the Planck spacecraft, though it remains uncertain whether these signals will be strong enough to detect, or whether interference from foreground sources might obscure them. Scientists are also hoping for future measurements of the so-called 21 centimeter radiation, light emitted and absorbed by neutral hydrogen before the first stars appeared. If successful, this method could measure the power spectrum of the early universe with even higher precision than current CMB and galaxy surveys. Yet it is unclear whether these observations will be possible, or if interference from radio sources both on Earth and throughout the galaxy will make them too difficult. In the early stages of inflation theory, Alan Guth proposed that the inflaton field responsible for driving inflation might be the Higgs field, the same field that gives elementary particles their mass. Later, however, many scientists came to doubt this idea. One major problem is that it conflicts with experimental results at the electroweak energy scale. Other models of inflation instead draw on ideas from grand unified theories, which attempt to unify the fundamental forces of nature. A key challenge for all inflation models is fine-tuning. For inflation to occur in the so-called new inflation model, certain slow-roll conditions must be satisfied. These conditions require that the inflaton's potential energy be extremely flat compared to the large vacuum energy of the universe, and that the inflaton particles themselves have a very small mass. In other words, the early universe must have had a scalar field with unusually special properties and initial conditions. Various explanations have been proposed for why such fine-tuning might naturally occur. For instance, classically scale-invariant field theories, in which scale symmetry is broken by quantum effects, can help explain the flatness of the inflaton potential, provided the theory can be reliably analysed through perturbation methods. Andre Linde introduced a different idea called chaotic inflation. In this model, inflation occurs naturally in almost any universe that begins in a chaotic high-energy state, as long as a scalar field with unbounded potential energy is present. Because the inflaton field in this scenario must take values larger than 1 Planck unit, These are known as large field models, in contrast with the small field models of new inflation. However, some physicists worry that in large field models, predictions from effective field theory may break down, as quantum corrections could be large enough to prevent inflation. This issue has not been fully resolved, and some researchers consider small field models, where inflation happens at lower energies, to be more reliable. Overall, inflation relies heavily on quantum field theory and semi-classical approaches to quantum gravity, but it has not yet been fully reconciled with these theories. Another fine-tuning concern involves the amplitude of primordial fluctuations, which depends directly on the energy scale of inflation. This scale is thought to be around 10 to the 16th giga-electronvolts, or about 1,000th of the Planck energy. Compared to the Planck scale, this is extremely small, representing a so-called hierarchy problem, though it is often not considered critical because it aligns with the scale of gauge unification. Many inflation models suggest that inflation never completely ends in the entire universe. Because inflating regions expand extremely rapidly, they can reproduce themselves, creating new inflating regions faster than they can decay into non-inflating space. As a result, at any given time, most of the universe's volume may still be inflating. All scenarios of eternal inflation lead to the idea of a hypothetical infinite multiverse, often with a fractal structure. This concept has sparked significant debate among scientists about whether inflation theory is fully viable. Paul Steinhardt, one of the pioneers of inflation, introduced the first example of eternal inflation in 1983. He showed that inflation could continue indefinitely by creating bubbles of non-inflating space filled with hot matter and radiation, surrounded by still inflating empty space. These bubbles could never expand fast enough to keep up with inflation. Later in the same year, Alexander Vilenkin demonstrated that eternal inflation is actually a generic feature of such models. Even in new inflation, where the inflaton field slowly rolls down its potential, quantum fluctuations can occasionally push it back up. Regions where the inflaton gains energy expand more rapidly than lower energy regions, eventually dominating the physical volume. Any inflationary model with an unbounded potential is therefore eternal. However, theorems show that inflation cannot continue forever into the past. The spacetime of inflation, similar to de Sitter space, is incomplete without a contracting phase. Unlike pure de Sitter space, fluctuations in a contracting inflationary universe collapse into gravitational singularities, points where density becomes infinite. This highlights the necessity of a separate theory to explain the initial conditions of the universe. In the idea of eternal inflation, certain regions of the universe continue to expand at an astonishingly fast exponential rate, while other regions, where inflation has stopped, do not grow in the same way. This leads to a remarkable conclusion. When looking at the universe as a whole, the parts still inflating are unimaginably vast compared to the regions that have stopped, even though from the perspective of an observer in a region that has already finished inflating, inflation eventually ends. The global picture shows that the inflating regions dominate the cosmic landscape overwhelmingly. Physicists have long debated how to make sense of this multiverse of different regions. If we measure probabilities by volume, one might expect that inflation never truly ends. On the other hand, if we impose a condition that a local observer exists to witness the end of inflation, then inflation should end as late as possible. Some researchers have tried to resolve this paradox by weighting observations according to the volume of space each observer occupies before inflation begins. Others argue that there is no satisfactory solution and view the concept of a multiverse as a fundamental problem in the inflationary theory itself. Notably, Paul Steinhardt, the scientist who first introduced the idea of eternal inflation, later became one of its most outspoken critics because of these very issues. Some scientists have proposed alternative models that attempt to sidestep the problem of initial conditions altogether. These models imagine a universe that has no true beginning, existing eternally while expanding exponentially on the larger scales. In such a scenario, the universe is spatially infinite and has existed forever, and it will continue to do so indefinitely. Other approaches focus on how the universe might have emerged from nothing, a concept explored in quantum cosmology. Alexander Vilenkin proposed one such scenario, while James Hartle and Stephen Hawking developed the no-boundary proposal, in which the universe naturally undergoes inflation from its initial state. Alan Guth famously described the inflationary universe as the ultimate free lunch. New universes, much like our own, could continuously form within an eternally inflating background, In this picture, gravitational interactions manage to bypass, without violating, the first law of thermodynamics, which governs energy conservation, and the second law of thermodynamics, which dictates the direction of time and the increase of entropy. However, while many agree that this approach solves some issues with initial conditions, others have raised objections. For example, it seems more probable that the universe could emerge from a random quantum fluctuation rather than from an eternally inflating background. Physicist Don Page highlighted a related concern. The thermodynamic arrow of time requires the universe to start in a state of extremely low entropy, which seems highly unlikely. In fact, according to this view, inflation might worsen the problem. The reheating process at the end of inflation increases entropy, demanding an even more perfectly ordered starting state than a conventional Big Bang without inflation. Hawking and Page later tried to calculate the probability of inflation occurring in the Hartle-Hawking initial state, but their results were inconclusive. Other researchers argue that in an eternal inflation scenario, the exact probability is less important. As long as the probability is not zero, once inflation begins, it will continue indefinitely and eventually dominate the cosmos. Physicists Albrecht and Lorenzo Sorbo offered an interesting perspective, suggesting that a universe with inflation is far more likely to arise from a random fluctuation than a non-inflationary one. The reason is that only a tiny amount of non-gravitational energy is needed to seed inflation, far less than would be required to create a universe without inflation, which outweighs concerns about entropy. Another challenge occasionally discussed is the so-called trans-Planckian problem. Because the energy scales of inflation are relatively close to the Planck scale, the realm where quantum gravity becomes important, some of the tiny quantum fluctuations that shaped our universe were initially smaller than the Planck length before inflation began. This suggests that unknown physics at the Planck scale could have affected them. Scientists disagree on how significant this effect might be. Some believe it could be barely detectable, while others think it may be completely hidden from observation. In addition to traditional models, a variation called hybrid inflation has been proposed as an extension of new inflation. Hybrid inflation introduces multiple scalar fields. One field drives the usual slow-roll inflation, controlling the period of rapid expansion, while the other triggers the end of inflation, when conditions become favourable for it to decay into a lower energy state. In this model, one field primarily determines the energy density and expansion rate, while the other dictates how inflation progresses and when it stops. Because of this arrangement, fluctuations in one field do not directly affect the other's role. When the second field reaches the bottom of its potential, it changes the first field's energy landscape, causing a rapid roll that ends inflation. This means that, unlike eternal inflation, hybrid inflation has a natural termination. Interestingly, the mysterious dark energy observed in the present-day universe resembles inflation in its effect, as it causes the expansion of space to accelerate. However, the energy scale of dark energy is far lower, about 10 to the negative 12 giga-electron-volts, which is roughly 27 orders of magnitude smaller than the energy scale of early universe inflation. In the quest to reconcile inflation with string theory, the discovery of flux compactifications was crucial. One such idea, called brane inflation, suggests that inflation occurs due to the motion of d-branes within a compactified higher dimensional geometry, often moving toward a stack of anti-d-branes. This scenario, described mathematically by the Dirac-Born-Infeld action, differs from conventional inflation and is still not fully understood. It appears that specific conditions are required, because inflation occurs through tunneling between two vacua in the string landscape, a process resembling old inflation, after which new inflation must proceed through a separate mechanism. Dark matter is a strange and invisible type of matter that we cannot see because it does not interact with light or any other kind of radiation. We know it exists not by seeing it directly, but by noticing its unusual effects on gravity. These effects cannot be fully explained by the usual laws of physics unless there is much more matter in the universe than what we can actually detect. We see dark matter's effect when we study how galaxies form and change over time, when light bends around very heavy objects, a process called gravitational lensing, and even in the way galaxies move inside groups. Its presence also shows up in the large patterns of the universe, and in the weak leftover radiation from the Big Bang. In the most widely accepted picture of the universe called the Lambda CDM model, All the mass and energy of the universe is divided roughly like this. 5% is normal matter, 26.8% is dark matter, and 68.2% is dark energy. This means that dark matter alone makes up almost 85% of all the mass in the universe, and together with dark energy, it makes about 95% of the total energy in the universe. Even after many years of study, scientists still do not know exactly what dark matter is. It seems to interact with normal matter and light only through gravity, which makes it very hard to detect with current tools. One main idea is that dark matter is made of tiny unknown particles, like weakly interacting massive particles, called WIMPs or axions. Another possibility is that dark matter is made of very old black holes that formed in the earliest moments of the universe. Dark matter is grouped based on how fast its particles move: cold, warm, or hot. Most scientists think dark matter is cold, meaning its particles move slowly. This slow movement lets dark matter gather together over time, forming structures that help shape galaxies and galaxy groups. While most astrophysicists are sure that dark matter exists, a small number of scientists are still doubtful. Some of them have noticed events that normal dark matter cannot fully explain. These scientists have suggested that maybe our understanding of gravity needs to be changed. They have proposed other ideas, like modified Newtonian dynamics or new types of gravity, but none of these ideas can perfectly explain all the evidence. This shows that even if gravity needs some adjustment, dark matter still seems to play an important role in the universe. The story of dark matter has a long and interesting history, full of discoveries and ideas from some of the smartest scientific minds. It starts in the late 19th century. In 1884, William Thomson, better known as Lord Kelvin, made interesting observations about the number of stars around the Sun. In a book based on lectures he gave in Baltimore, Kelvin estimated how stars moved near our solar system and guessed what might happen if there were 1 billion stars within 1 kiloparsec of the Sun. At that distance, stars would move in ways that were hard to explain, suggesting there could be invisible matter in space. Lord Kelvin also estimated the Sun's age to be between 20 and 100 million years, a number later found to be far too low. But his curiosity about the movements of stars helped start early ideas about dark matter. About 20 years later, in 1906, the French mathematician and physicist Henri Poincaré used the term dark matter, or matière obscure, while discussing Lord Kelvin's work. Poincaré suggested that there might be hidden mass in the universe, though he thought it was less than the amount of visible matter. While his ideas were not completely correct, his mention of dark matter brought the idea into scientific discussion. In the 1920s, astronomers kept studying the idea of dark matter. In 1922, Dutch astronomer Jacobus Kapteyn was among the first to use the speeds of stars to suggest that some invisible mass might exist. He noticed that the movement of stars seemed affected by unseen forces, hinting at hidden matter. Then, in 1930, Swedish astronomer Knut Lundmark expanded on this idea, realizing that the universe must have much more mass than what telescopes could see. This was an important step, showing that the visible universe might not tell the whole story. In 1932, Dutch astronomer Jan Oort studied the movement of stars near our galaxy and suggested that dark matter could exist in our galactic neighborhood. He concluded that our galaxy must have more mass than we can see. Later, Oort realized that his measurements were not completely accurate, and more research would be needed to find the true nature of this invisible mass. Then, in 1933, Swiss astrophysicist Fritz Zwicky made a big breakthrough while studying galaxy groups at the California Institute of Technology. He looked at the Coma cluster, a large group of galaxies, and found something surprising. The galaxies were moving much faster than expected based on the visible mass alone. Zwicky suggested that there must be a huge amount of invisible mass, which he called Dunkelmaterie. He estimated that the Coma cluster had about 400 times more mass than could be seen through telescopes. This unseen mass, he said, was responsible for the gravity holding the galaxies together. Even though Zwicky's numbers were off because of old data, he was one of the first to realize that the universe contains invisible mass that affects gravity. Zwicky thought dark matter was normal matter that just did not give off light, unlike today's view that dark matter is something completely different and mysterious. Still, his work marked an important step toward our current understanding. Over the next years, more proof for dark matter started to appear. In 1939, H.W. Babcock studied the rotation of the Andromeda Galaxy. He found that stars at the galaxy's outer edges were moving much faster than expected, suggesting far more mass than could be explained by visible stars. At first, Babcock thought the unusual spinning might be caused by light being absorbed in the galaxy, or by differences in the outer regions, but his observations hinted at the presence of invisible matter. In 1940, Jan Oort made another key discovery. While studying the galaxy NGC 3115, he found a large, unseen halo of mass around it, further suggesting that galaxies are filled with hidden matter beyond what telescopes can see. The idea of dark matter really started to gain attention in the 1970s. Different scientific findings came together and suggested that galaxies might be surrounded by huge, invisible halos of matter. In 1974, two separate research groups, one from Princeton, New Jersey, led by Jeremiah Ostraker, Jim Peebles, and Amos Yehiel, and another from Tartu, Estonia, led by Jan Einasto, Ensar, and Ants Kasich, reached the same conclusion on their own, which made the idea stronger. One of the first clues that galaxies are surrounded by invisible halos of matter came from observing how they spin. Both traditional observations with visible light and studies using radio waves were key to these discoveries. In the late 1960s and early 1970s, Vera Rubin and Kent Ford used a newly developed spectrograph to measure the speeds of stars in edge-on-spiral galaxies more accurately than ever before. Their measurements produced surprising results. The outer parts of galaxies were spinning much faster than expected based on the visible matter alone. Around the same time, radio astronomers were making their own discoveries. Using advanced radio telescopes, they studied the 21-centimeter emission line of atomic hydrogen in nearby galaxies. Unlike stars, which are concentrated in the inner regions of galaxies, hydrogen gas extends far beyond the visible edge. This allowed scientists to measure the rotation of galaxies at much larger distances, giving a clearer picture of the galaxy's total mass. Early observations of the Andromeda Galaxy, made with large instruments such as the 300-foot Greenbank telescope in the United States and the 250-foot Jodrell Bank dish in England, revealed that the rotation of hydrogen gas did not follow the patterns predicted by Kepler's laws, which describe how objects orbit around a central mass. As technology improved, astronomers could make even more detailed measurements. In 1975, Roberts and Whitehurst measured the rotational speed of the Andromeda Galaxy all the way out to 30 kiloparsecs. To their surprise, the galaxy's rotation curve stayed flat, even at these great distances. This suggested that there was far more mass present than what could be seen with ordinary telescopes. By combining optical measurements of stars with the new hydrogen data, their charts showed a clear difference. The curve representing the star's light remained the same, but the curve representing the total mass continued to rise even in the outermost regions of the galaxy. Meanwhile, scientists were developing even better methods to map galaxies. In 1972, Rogstad and Shostak used interferometric arrays, networks of several radio telescopes working together, to chart the hydrogen rotation curves of 5 spiral galaxies. They discovered that all of these galaxies also had flat rotation curves, reinforcing the idea that the mass in the outer regions of galaxies was much larger than could be accounted for by visible stars. By the late 1970s, the idea that galaxies were surrounded by halos of invisible matter, now called dark matter, was widely accepted, even though its nature remained mysterious. Throughout the 1980s and 1990s, many observations strengthened the case for dark matter. One of the most significant studies, conducted by Persic, Salucci, and Stell in 1996, examined 967 spiral galaxies and found strong evidence supporting the existence of dark matter. Additional evidence came from effects like gravitational lensing, where the gravity of galaxy clusters bends light from more distant objects, from the distribution of hot gas in galaxies and galaxy groups, and from tiny temperature differences in the cosmic microwave background, which is the faint afterglow left over from the Big Bang. Today, most scientists believe that dark matter is made of unknown particles unlike anything we have detected so far. Finding these particles is one of the biggest goals in modern particle physics, and researchers are using a variety of methods and experiments to try to identify them. In simple terms, matter in the universe refers to anything that contributes to the total energy and whose density decreases in a specific way as the universe expands. As the universe grows, the density of matter decreases in proportion to the cube of the expansion, meaning that as space stretches, matter becomes thinner. Radiation, such as light or high-energy particles, decreases even faster because its energy weakens as the universe grows, following the inverse fourth power of the expansion. The cosmological constant, on the other hand, is different. Its energy density does not change as the universe grows, because it is a property of space itself rather than of matter or radiation. This difference arises from what is called redshift. If the size of the observable universe doubles, the scale of expansion doubles as well. Light from the cosmic microwave background stretches over this larger space, so each photon loses energy. Fast-moving particles, like neutrinos from the early universe, lose energy in the same way. But the energy density of the cosmological constant remains constant no matter how large the universe becomes. Dark matter generally refers to parts of the universe that we cannot see directly, but which still have mass and behave similarly to normal matter. In many cases, it refers specifically to an invisible type of matter that is not made of the familiar particles we know, excluding ordinary missing matter called baryons. Depending on context, the term can have slightly different meanings, but the core idea remains the same. There is unseen mass influencing the universe. The arms of spiral galaxies rotate around their centers, and as one moves outward, the visible mass from stars decreases. If galaxies only contained visible matter, their rotation would follow the same pattern as planets in the solar system, slowing down as they moved further from the center, according to Kepler's third law. But observations show something different. Stars and gas in the outer parts of galaxies continue to move at roughly the same speed as those closer in. This tells us that the mass in spiral galaxies is spread out very differently from systems like the solar system. It implies that a large amount of invisible, non-light emitting matter, dark matter, exists, especially in the outer regions of galaxies. Astronomers also use the virial theorem, a rule connecting the speeds of stars to the total mass of a system, to study how mass is distributed in galaxies and dense star clusters. When they measure stellar speeds in elliptical galaxies or star clusters, they often find discrepancies. The visible stars alone cannot account for the observed motions. Just like with rotation curves, the most likely explanation is the presence of additional invisible matter, or dark matter. Galaxy clusters are particularly useful for studying dark matter because their total mass can be measured in three ways. First, by observing the range of speeds at which galaxies within the cluster move. Second, by examining X-rays emitted by hot gas inside the cluster. These X-rays reveal the temperature and density of the gas, and using the balance between gravity and pressure, scientists can estimate the cluster's total mass. Third, through gravitational lensing, where the cluster's gravity bends light from more distant objects, allowing researchers to measure the mass without needing to track individual galaxies. Together, these methods provide compelling evidence that most of the mass in galaxies and clusters is invisible, confirming the existence of dark matter. All three independent methods of study, whether through observing motion, bending of light, or the cosmic microwave background, point to the same striking conclusion. Dark matter makes up about 5 times more mass than all the ordinary visible matter combined in these clusters of galaxies. This means that most of the matter in these huge cosmic structures is invisible to telescopes, and we can only detect it through its gravitational effects. One of the most fascinating predictions of Albert Einstein's general theory of relativity is gravitational lensing. This effect happens when a massive object, like a galaxy or a cluster of galaxies, sits between a distant light source and an observer, such as us on Earth. The massive object acts like a cosmic magnifying glass, bending and distorting the light from the source. What is important here is that the bending depends only on the mass of the object, not on what the object is made of. The more massive it is, the more it bends light. For example, if a group of galaxies lies between us and a very distant quasar, the gravity of these galaxies bends the light from the quasar, changing the way it appears to our instruments. There are 2 main types of gravitational lensing. Strong lensing happens when the bending is dramatic enough to create long arcs or multiple images of the same background object. This effect has been observed around many distant galaxy groups, including a famous one called Abel 1689. By carefully studying the shape and size of these arcs, scientists can calculate how much mass is in the lensing galaxy group, including the dark matter that cannot be seen. On the other hand, weak lensing is much subtler. Galaxies in the background do not turn into arcs, but are slightly stretched or distorted. By measuring these tiny distortions across large areas of the sky, astronomers can map out how dark matter is distributed throughout the universe. In fact, the patterns of mass revealed by lensing closely match predictions made by studies of dark matter. Even though dark matter and ordinary, normal matter are both types of matter, they behave in very different ways. In the early universe, ordinary matter was made of charged particles that interacted strongly with light, which caused it to scatter and slow down its clumping. Dark matter, however, does not interact directly with light but still has gravity. This means that dark matter could start clumping earlier, forming gravitational wells that influence the surrounding ordinary matter. Dark matter also leaves its mark on the cosmic microwave background, or CMB, through gravity, affecting large-scale structures and the motion of normal matter. As a result, dark matter and ordinary matter evolve differently, leaving distinct signatures on the CMB that astronomers can study. The cosmic microwave background itself is an almost perfect blackbody radiation, which means its temperature is nearly uniform in every direction. But there are incredibly tiny variations, about 1 part in 100,000, that scientists call anisotropies. By mapping these tiny temperature differences across the sky, astronomers can create a graph called the angular power spectrum, which shows peaks and valleys representing the sizes and intensities of the variations. The positions and heights of these peaks reveal important information about the contents and evolution of the universe. The first discovery of these uneven patterns in the CMB was made in 1992 by the COBE satellite, but the images were too blurry to show the detailed peaks. In 2000, the Boomerang experiment, which used a high-altitude balloon to take measurements, detected the first of these peaks. Later, satellites such as WMAP and Planck measured the CMB with much higher precision. These measurements strongly supported the standard model of cosmology known as lambda CDM, confirming the essential role of dark matter in shaping the universe. The formation of structure in the universe began shortly after the Big Bang, when tiny differences in the density of matter caused gravity to pull matter together, eventually forming stars, galaxies, and clusters of galaxies. Before this time, the universe was remarkably smooth and uniform, with almost no density variations, as described by the Friedmann solutions to Einstein's equations of general relativity. As time passed, these tiny differences slowly grew and merged, gradually transforming the smooth early universe into the complex cosmos we see today, filled with stars, galaxies, and enormous clusters. In the early stages, radiation dominated the energy of the universe and had a strong influence on ordinary matter, preventing it from clumping together efficiently. If only ordinary matter had existed, there would not have been enough time for these tiny fluctuations to grow into the large structures we observe today.